afternoon.
Thank you. Sorry.
Yeah.
Anyone else? And all good?
Yeah.
Okay. So over to you, James.
Yep, so morning everybody. So yeah, I'm James Coop. I'm presenting on behalf of a former PhD student of mine who's called Wadi, who's now based at Mayerdal University. So the talk is going to be a bit different from perhaps you've been hearing about in the last couple of days, in the sense it's not about open channel flows, it's not about rivers, and it's also not about the development of methods either. It's more about exploring how we can use surface image velocimetry to look at the spatial dynamics of shallow overland flows that occur on hill slopes and trying to link that with the microtopography. Let's go on to the next slide. So if we just play that video. So this is a video just showing some rainfall simulation experiments that we've been doing in Japan, where you'll just see that this plot is going to be exposed to a pretty extreme rainfall event, a duration of 20 minutes and a high rainfall intensity of 120 millimeters per hour. And this is the kind of problem that we're trying to address, is how can we understand the dynamics of these flows, in the sense that very early on in that video, you'll see that you get development of Portonian overland flow. That flow area of inundation then expands through time. This develops micro rills, and those micro rills get larger through time, they coalesce and form much larger rills that are forming at the very base of the slope. And of course, the issue with this is, how do we go about measuring those dynamics? Go to the next slide, please. And the issue is these flows are very shallow. So we're talking about a few millimeters up to a few centimeters. And in terms of relative submergence, which I define in terms of the depth of the flow divided by the roughness height, we're talking where the flows are predominantly a submergence of less than 1, all the way up to around about 5. So quite different from what you would see in an open channel flow or a river flow. So the tricky thing is how to go about measuring those dynamics, is you can't put an instrument in the flow itself, because of course it disturbs the flow and causes local scale. So you can't use something like an ADV. But the issue is actually making sure you're able to capture that event. So for example, on the bottom right hand corner, you'll see that's where a very large rill is developed in an agricultural field. The conditions are exactly the same throughout the whole of that field, the same slope, same soil conditions, same rainfall events, but you just get a rill developing in one area of that field and nowhere else. And even on the sort of catchment scale, here again, land use, vegetation, so on, all very similar, and yet you've only got this overland flow occurring in just one section. So the issue is in the field is about trying to ensure that you put your instruments in the right place, otherwise you just completely miss the rainfall event, the overland flow event. That's the next one. So of course, the way in which people tend to, a common approach to get around this is to construct plots, such as in the top left and the top right hand corner, in the sense that you can either generate your own rainfall event, so you guarantee that you can measure that overland flow within your plot, or you just try and put as many plots in as you possibly can within your field of interest, with the idea that you hopefully therefore capture that event. But then of course those rules, those plots that you put in place, of course, are then going to influence the development of that overland flow, and then any kind of subsequent rill development that occurs because of that event. And the other thing is, because it's tricky to measure, then what they just tend to do is just measure the discharge that's coming off the plot, which of course tells you nothing about what's happening within the plot itself. It doesn't tell you anything about the dynamics, doesn't tell you anything about how those dynamics change with the microtopography. We just do that video on the bottom right. So of course, one idea is, as we did in Japan, is you can get your postdocs and PhD students to perilously sit and walk along a ladder across your plot during the rainfall events and do some very simple rudimentary measurements of injecting some dye and simply measuring the time it takes for it to move over a known distance. But of course, this is just giving you ballpark figures, very limited information really on the velocity field, how that links to the microtopography. So clearly there's got to be other approaches. And so of course, that's why I'm here, because we all agree that surface velocimetry gives us the ability to be able to measure these dynamics. So I'm going to be presenting how we've done that and what kind of new understanding we've gained from using surface velocimetry. Okay, so the other attempt I just want to is using flumes. This is the other approach. Now people who do soil erosion work use flumes in a very different way to how we would do, let's say, looking at a river channel, where we would just look at the flow within, let's say, the central third of the flume. In those kind of flume studies, they're actually using the walls of the flume as a proxy for the walls of the rills. Okay, so of course the relative submergence tend to be very deep, and of course these kind of simplified geometries really don't reflect the kind of real development that you get out in the field. Next slide, please. So of course, one of the problems is then people have had to make assumptions about the dynamics of these overland flows, because they've got this limited information on the dynamics. So the common approach is to assume that those flows are steady, they're uniform, and of course, demonstrably they're not, but therefore they're using open channel flow resistance equations to try and model these overland flows. So whether it be something like the Manning's equation or the Darcy-Weisbach equation. And the consequences of that is, if you want to then be able to work out soil erosion rates and model those soil erosion rates, you get these very simple relations between the discharge that's coming off the block and the slope of the particular hill slope, and then calibrated with some kind of coefficient beta. And the other approach is that the problem is that they're using sediment transport equations developed for rivers. So whether it be like the Einstein-Brown equation, which is basically that simple form there, or whether it be any kind of other transport capacity equation like the Meyer-Petter-Muller equation. And the other assumption using these equations with having a roughness coefficient is the assumption is that roughness is uniform, that grain roughness is uniform, and also that form roughness can be ignored. Now, of course, go on to the next clip. And of course, the thing with eroded hill slopes is its multi-scale roughness, from the grain scale where you get cratering due to the impacts of raindrops on the surface, all the way through to the micro rills and then the much larger rills that develop through a rainfall event. So of course, not only is grain roughness important, but also form roughness, such as on the right-hand side, also becomes important in the dynamics. Next one. And the other assumption in these equations is that these flows are independent of relative submergence. Now, the way in which you correct that is to correct it based on the friction factor, or the Manning's number, and allow for relative submergence. But of course, those corrections are based on relations developed for open channel flows and pipes. And to illustrate why that's a problem, we just go to the next click, is what I'm showing you here is the conveyance, the inverse of flow resistance on the y-axis against relative submergence, defined as the depth of water divided by the roughness height. Now, the dashed red line is the Manning's number, which has been corrected for the relative submergence. And then the curved line is the Quilligan equation for correcting the Darcy-Weisbach friction factor. And you'll see at relative submergences of 10, you get a divergence between those two fitted lines. But more importantly, as you'll see over the range of relative submergences that you get for overland flows, so up to around about a relative submergence of 5, you can see that that flow resistance tends to infinity. So in other words, you can't correct for the influence of relative submergence through these equations that have been developed for open channel flows and pipe flows. On to the next one. So of course we now, hopefully convince you we need to actually understand a little bit more about the dynamics of these flows. So we conducted some quite simple experiments where we constructed a 2.4 by 1.2 meter erosion plot, basically a big soil box really. And then we simulated a rainfall event using a couple of nozzles of duration of 20 minutes and a rainfall intensity of 110 millimeters per hour, generating Ortonian overland flow and then developing rills and micro rills on that surface. And we repeated that for 5 different slopes so we could generate different topographies. And we used a local soil to Liverpool, so that the soil had a D50 of 0.3 millimeters, and we had a GoPro camera and a white light source for doing some surface PTV, and we seeded that with buoyant particles. Okay, so we then used structure from motion to measure in detail the topography of these surfaces. To give you a sense, we were getting the point cloud density was around 25, on average 25 points per millimeter, so sub-millimeter resolution. We just go to the next clip, and you'll see there's quite a progression in the change in the topography from the lower slopes through to the higher slopes. So even on the low slopes, 5%, you'll see, okay, it's reasonably flat, but you're still getting these micro rills developing. Whereas, just go to the next clip, whereas if we go to the higher slope, we start to get these rills developing. These rills were typically in depth around about 10 to 30 millimeters, and in terms of width, varying between 50 and 200 millimeters. Go to the next one. And so what we can do is just use those DEMs to characterize the grain roughness in terms of the standard deviation elevations, which is the plot on the left-hand side, and also in terms of the range in bed elevations. And you can see, as you might expect, as you increase the slope and therefore you get in that progressive development from micro rills to rills, that surface obviously becomes much rougher, more complex and more organized. And that's reflected in those trends in grain roughness. Okay, and then we can also not only just look at a single metric of roughness, but also look at how the local roughness changes over the plots. There's just an example from that high slope where we have the rills that are developing. And we can look at how the distributions of local roughness changes for our different slopes. So the lowest slope being S1 and the highest slope being S5. And the idea of this is you're looking at how the roughness changes within a grid of 10 by 10 millimeters, which for our soil relates to around about 30 E50. And you'll see that all of these distributions are positively skewed, and they become more and more positively skewed as you increase that slope, reflecting that greater complexity. Okay, so we use we used a Mosaic, which is an Imagery plugin for doing our surface PTV. So you'll see a stacked image here on the left-hand side, and we use that in order to mask out the areas of no flow and flow, and then we applied the PTV, which was done at, so we collected imagery at 80 frames per second for 120 seconds, and then we gridded those resultant trajectories into a 10 by 10 millimeter grid, and that was really a balance between having a sufficiently large size that we have enough tracks within that particular grid to get a good time average, versus it being too large that you're actually averaging out any of the kind of spatial information that you're interested in. And then we're then able to georeference the structure from motion digital elevation model, then with the flow measurements that we got from our surface PTV. So we could georeference and look at the correlation between the topography and the flow. Okay, so we can obviously start to just eyeball what that correlation is, but what we wanted to do is actually try and quantify the correlation between the microtopography and the flow, but just so you sort of get a sense of how we did 3 different discharges. We fixed those surfaces so the surface didn't change for each of those 3 different discharges that we generated over the eroded surfaces. And you'll see, as you might expect, as you increase that discharge and therefore increase the submergence and increase the Reynolds number, is you get a number of other threads of flow developing. You get that increase in inundation in that area. But of course, we want to try and quantify that correlation rather than just eyeballing it. So what we did was just some simple cross-correlation. And so we did a simple cross-correlation between the streamwise velocity and the elevation, the bed elevation. And then we plotted that against our different factors. So in terms of slope, and those 2 grain roughness factors or metrics, the standard deviation in elevations and also the range in elevations. And these are correlation coefficients. So +1 is going to be a perfect positive relationship, correlation, and -1 being a perfect negative and 0 being, well, virtually no correlation whatsoever. So what you'll see is at the very low slopes, in other words, low roughness values, as you might expect, the level of correlation is actually pretty poor. But as you increase that complexity and you get those development of rills and the concentration of flow within those rills, that correlation begins to steadily rise up to a reasonable level of correlation. That's in terms of elevation, but we can then repeat that and see how that streamwise velocity is correlated to the local roughness, i.e. how those elevations change within a 10 by 10 millimeter grid. So if we look at those correlation values, you'll see that they're much higher when you start to look at that spatial organisation, local organisation of those elevations, the local roughness. You're getting these much higher correlation values. You'll see, although the plot in some ways suggesting that these are varying quite significantly with roughness, if you can compare the range of values on the top to the range of the values at the bottom, you'll see that actually there's a fairly consistent level of correlation regardless of the slope or the roughness in this case. Although, of course, there's a slight trend for a decrease as you increase those roughness values. And then what we also then did was use those flow measurements to start to look at the Darcy-Weisbach friction factor and to see the kind of the factors that influence the level of flow resistance. So here we're showing that Darcy-Weisbach friction factor in terms of those two grain roughness parameters. And you see, as you might expect, that flow resistance is increasing with grain roughness. But the most interesting one, just go on to the next plot, is to have a look at how the friction factor changes with Reynolds number. So we had the 3 different discharges, and our Reynolds number was increasing with each of those discharges. And what you would expect in an open channel flow is the exact opposite as to what we see here. You'd expect an inverse relationship between the friction factor and the Reynolds number. But what you actually find at these much lower submergences, so particularly at the very low Reynolds numbers where you get a relative submergence of less than 1, so you're getting marginal or partial submergence of the roughness elements, is what you actually get is an increase in the flow resistance with the Reynolds number. Now, the reason behind that is in an open channel flow where typically the submergence is always going to be greater than 1, so all your roughness elements are submerged, is as you increase the Reynolds number, the frontal area of the roughness elements that's exposed to the flow, the projected area, is going to remain constant regardless of the change in Reynolds number. So in other words, flow resistance is going to reduce with an increase in the Reynolds number because you're getting that increase in relative submergence. Whereas in overland flows, because your submergence is less than 1, as you increase that Reynolds number, the projected area of those roughness elements exposed to the flow will increase with an increase in the Reynolds number. And that accounts for that upward trend for these low submergences. Now, if we'd continued these tests and perhaps done a much higher Reynolds number, then you might have expected it to go back down, as you might expect for an open channel flow. So in other words, with overland flows, the feeling is we're more likely to get a convex upward curve with Reynolds number. So then we thought, right, okay, it seems like drag's going to be important. If the projected area, frontal area of those roughness elements is changing with Reynolds number, then of course drag is also going to be increasing. And that is likely to account for that increasing trend with Reynolds number. So using our flow measurements and our digital elevation model, we could obviously work out what the frontal areas were and figure out how those change with discharge and how they change with Reynolds number. So what you'll see is that the drag is concentrated within the rills, as you might expect, but particularly the walls of the rills and also the junctions at where rills meet. And of course, as you increase the Reynolds number, the area of drag that exists within the plot, of course, increases because the submergence increases. That's as you might expect. Just go on to the next slide. But what we wanted to do then was just look at how the distributions, the drag distributions, change with roughness and change with Reynolds. So we're just showing you some examples of the drag distributions there for our 5 different surfaces at the 5 different slopes. And we wanted to sort of quantify how the shape of those distributions changed with our parameters. So we fitted a viable distribution, a 2-parameter viable distribution to these drag distributions, where you have 2 parameters. You have a scale parameter and you have a shape parameter. Now, if you increase the scale parameter, then you're shifting your distributions to the right-hand side. And if you increase the shape parameter, then you're narrowing those distributions. So by having a look at how those parameters change with roughness, we can get some sense of how those drag distributions are therefore changing. Next slide. So here we've got the scale parameter, how that changes with our 2 grain roughness metrics, and likewise with the shape parameter on the bottom. So the scale parameter is increasing with roughness, the shape parameter decreases. Now, if we take those results together, what it's showing is as we increase the roughness, is those distributions, drag distributions, are getting much wider. And also we're shifting everything to the right-hand side. In other words, we're getting a higher proportion of areas experiencing higher drag as we increase the roughness of the eroded soil surface. Sorry.
So we're running very short in time.
Yeah.
Short for 20 minutes.
Okay.
Yeah.
I can do it very quick on the next one.
Yeah.
So just to summarize, hopefully I convinced you that you can't use open channel flow resistance equations. You know, these 1D uniform steady flows assumption doesn't hold for overland flows. We've got to really start to think about relating flow resistance and erosion thresholds to not only grain roughness, but form roughness, particularly the development of micro rills. And then next one, please. And really the challenge for you guys is we've got to start to not look at just what's coming off the plot, but what's happening within the plot, what's happening within the field, what's happening within the catchment, thinking about how we can go about measuring the unsteady nature of these flows as they develop through time, whether it be in your field in order to understand soil erosion and pollutant dynamics, or whether it be to understand things like highway runoff and the contribution of these overland flow events to pollution in urban areas.
Right. Any questions while the next speaker is setting up? It's Guillaume.
Yes, thank you for this presentation. I have a question about the measurement of the microtopography. Do you do it at different time during the rainfall simulation, or was at the beginning and at the end?
Yeah, so we did it for these particular tests. We did it at the beginning and the end because we didn't want to stop the rainfall event because that could potentially obviously influence how the topography develops. But in some separate tests, we did do exactly that. So we did a much longer duration of events of 60 minutes, and every 10 minutes we did those microtopography measurements, so we could see how that developed through time.
And how do you measure the water depth? How do you measure, especially the water depth?
Yeah, so we did a laser scan of the water surface. And so knowing the elevation of the eroded surface below and knowing that's fixed, then obviously we could then calculate the depth.
Okay, using the
Yeah, that's right. Yeah.
Any questions online?
No.
No. Okay, so I'm sorry, that's
fine.
probably difficult.
Thanks.
Next up is Guillaume, who's going to show us a very nice.
Yes. Oh, really? Sorry, let me just get off this. What? Yeah, great. And then just with this, right? Okay, yeah.
Hello, everybody. So I'm Guillaume Bodard, a PhD student working on several improvements regarding the LSPIV methods. My supervisors are the developers of food LSPIV, so Jérôme Lecause, Alex Soet is here, and Magali Jodot. So today I'm going to talk a bit about synthetic flow videos for evaluating image-based velocimetry. So first, a little bit of context. So as you may see, image-based methods are growing faster, either to determine velocities for velocity mapping or for discharge estimation. But still, one constant that remains is how to properly evaluate these methods. So what I mean about evaluation process is comparing the velocity results, so this image-based method, to a reference in given situations. And the problem that we face actually is that the on-field conditions are often imposed in terms of illumination, for instance, water aspect, or tracers properties, flow density, whatever. Tracer densities or flow properties. And we also have a problem with the reference. So the velocity reference that we're using have some uncertainty and are most of the time acquired only along a transect. So it it is limited to evaluate the whole 2D velocity field. So an interesting situation to overcome this limitation is synthetic imaging. So with synthetic imaging, the advantage is that you control all the conditions and you know exactly the velocity reference. So several contributions in the field of image-based method are based on such synthetic inputs. So either to investigate optimal setup regarding the parameters, or to validate methods, or to carry out sensitivity analysis. So what motivated this work is the ability to study environmental error sources. So we'd like to know, for instance, how the water aspect coupled with the angle of the camera are impacting the velocity. So for that, we have to be able to reproduce a scene, a measurement scene. So realism is the main concern of this work, and also the ability to play with the configuration, so the illumination, the scene environment, and so on. So the method that we proposed, next slide please, is based on computer graphic tools. So Blender and Mentaflow. So Blender is a 3D creation suite that allows to create a synthetic scene, artificial scene. So we can place several elements. Mentaflow is used. So Mentaflow is a fluid simulation library that is dedicated to computer graphics. And Mentaflow is embedded into Blender, which makes it more convenient to use. So then we simulate the flow, and then after that we can set the water aspect, place some GCP's objects, place the camera on the scene, and render the image through the artificial camera. So we get the synthetic video. And then after that, we build up a framework to extract surface velocities from Mentaflow simulation. Next slide, please. So now we'll detail all the steps. So the first step is to create the channel. So here with Blender, we can digitally sculpt the channel. So there's also the possibility to import 3D formats. So we have meshes that are already built. So here I build the channel. I place some GCP's objects that you can barely see here. Here I place the mean flow and the weir just for the simulation. Next slide, please. Then we set up a domain, simulation domain on the scene. And with Mentaflow, we carried out the fluid simulation. So the fluid simulation is based on Navier-Stokes equation, and it uses half grid and half particle based framework. So the idea, I try to summarize it quite quickly. So here you can see on the ZX projection of a grid. First, the velocities are computed on a grid and stored in this grid, and these simulation velocities are used to displace the particle at each time step. So when you generated this, you can click on this image. After generating the particles, you have does not work.
No, it's not.
Yeah. No problem. We'll see later. Yeah. Next slide, please. So then when we have these particles, what we need at the end is to get an object, a fluid object. So we have to define it, to get a close control around this object. So we build a mesh around these particles. So here is an example of mesh built around the particles with several parameters. So here we have the mesh resolution. So we obtain this kind of object. Here it could be, which one? You cannot, if you stay.
I'm sorry, I had some videos to show. Yeah, I think it's on Chrome. Yeah.
Here we are. So here we have the mesh that is built around the fluid particles. Maybe I would stay with this presentation. Can I get back? Can I get back to the presentation? Yep. Okay, so that was a bit long. Sorry for that. So then when we have the mesh, now we have the mesh. So we have a fluid object at each time step. Next slide, please. So now that we have that, the idea is to set up the scene aspect. So Blender made it very easy because we can use the scene environment images. So these are 360 degrees images that defines the scene environment and the lighting. So here you have an example. So our scene is placed in the middle of this image. It's a bit difficult to see, but thanks to that, you can simulate various scene environments. So here you have the scene that is placed in there. So we have various lightings and scene occlusions that can be reproduced with this approach. Then you configure the camera. You can use various types of cameras with various focal length or parameters. And you can set up the water aspect. So you have various aspect properties. So you have many possibilities with Blender. This is quite amazing. So next slide, please. Then right after that, so we have built our fluid objects. We have set the scene parameters, rendered the artificial sequence through the virtual camera. Now this is the process that we use to extract surface velocities. So as I said before, you have the reference velocities from simulation that are computed on a grid. Here they are. You have the mesh with the yellow in yellow here. And so what we can do is interpolate the reference velocities at the mesh vertices. So you obtain these yellow velocities. So at each mesh vertex, we'll have the reference velocity. Then we filter out to retain only the surface velocities. And as the mesh vertices are moving through time, we are interpolating these velocities on a regular grid so that we can compare these velocities on a fixed grid with the velocities from LSPIV, for instance, or other methods. So here is an example. You have the velocities that we obtain for one time step. And here is the time average velocities that is plotted on the whole domain. Next, please. So there's one thing that I'd like to emphasize, one kind of limit or problem that we find out with this method is that, as I've shown before, the reference velocities are computed on a grid. And these reference velocities are used to displace the particles. And then we build up a mesh around the particles. So this means that the reference velocities are not directly moving the mesh. But this is the mesh that we can see. I don't know if you exactly understand the point. So what I mean is that there could be a difference between the apparent velocities, so the apparent movement of the mesh, and the reference velocity. This is an example of error in case of a too large mesh resolution. We'll have an aspect that the mesh will not represent correctly the particle movements. So we may have differences between the reference velocities and the velocities that we can see and that we can measure. So this is a problem, and the reference velocities are not known prior, and the precision neither. So this is a problem, but we found out that with a resolution that is high enough or thin enough, we reduce this problem. So I'd like to show you a case study first. Next slide. So yeah, the resolution is very important, and we find out that with very thin resolution, we limit the problem that I just exposed before. So this difference between the reference velocities and the apparent velocities. But also we ensure very high realism. So here we carried out a split simulation on a domain of about 30 meters and 6 meter wide with a resolution of 4 centimeters per cell. So quite a high resolution. And it takes almost 3.5 days to compute. But then the advantage is that with this simulation, we can generate many different scenes or many different water aspects. So we can play with a lot of error sources with just one simulation. Next slide, please. So just to emphasize this kind of difference that I mentioned. So we carried out a test with LSPIV applied on these images. So to reduce the potential error sources, we use orthographic camera, which means that there is no perspective. So this is a very simple scaling. We know exactly all the data. And first, we applied LSPIV on the particles. So we have highly contrasted particles, and we obtain very good results. So the results are within the LSPIV uncertainty. So we can see that there is a good agreement between the measurement and the reference velocities. And then we use the same things, only we use the mesh around the particles. And you can see that there is a little bias. And so this bias is about 2% on the average velocity. So this is not big, but these translate the limitation that I expressed before. Next slide, please. So that was about the computation. Now this is the movie time. I'm going to show you some results that we can have. So can you please click on?
Think about it.
Yeah, you will have to fix it. So here are many cases that were generated with only one simulation. Just by playing with the scene, here are the scene environment images. And you can see that here is the mesh view. And then using these different environments, we have different water aspects. Can you please click on this one? So here is the colors are not super great, but at least you can see what we have in this situation. So
And then, I don't know.
how to escape?
Yeah.
Would you like that?
Oh, you don't have your 3D glasses. So here you can see that we reproduce the noise at the water surface. We have various traces, densities, some reflections. Great. So
On the next one.
yeah.
It might reload the presentation again.
Okay.
I'll just have to go there.
Okay.
Which one?
Yeah, I'll go. I don't know how I am on time. Maybe I won't show everything, but as you can see, we can reproduce many configurations. And so this is an example from one point of view. Then I've built some other, for example, from a drone here. And you can see that, yeah, actually the surface waves are quite accurately reproduced. Then I won't bother with many images, but another thing interesting, we can also reproduce shaking, camera shaking, for instance. So yeah, Blender offers really many possibilities. And with that, we can, answer many questions and a practical question, like for instance, how the GCP distribution, how this distribution impact the final measurement. Or we can study or validate new methods or carry out sensitivity analysis. So this is quite interesting. We are. Yeah, another one here with shadow. So yeah. So if you're interested, I can share all the data set. I'm actually building up a large data set with various conditions. And so, yeah, here are the conclusions. So we see that we obtain quite an interesting realism with these tools, and we can, investigate a lot of various on-field situations. Then the actual limit or the time consumption for simulation, but these can be, we can play with it. So actually the simulation are performed on only one computer. We can do this simulation on a computer cluster, for instance. And then this is not completely a problem, as from one simulation, you can generate a lot of various situations, as I just showed. Then there is this reference velocity problem. So actually, we find that the bias is about plus 2.5%. So we can at least get an estimate of this bias. And yeah, still, so computer graphic tools are promising, as we can see. So many things we investigated, especially with Blender. So there are many plugins in the very large community. Mentaflow also, actually, we used a very simplified version of Mentaflow that is exposed to Blender. But you have, for example, a surface turbulence module or K-epsilon turbulence module that are also embedded into Mentaflow that could be used, or even another simulation engine could be used. And yeah, the opportunities are validation study, comparative studies, of course, uncertainty analysis. Next slide. Yeah, that's all. Thank you.
Any questions? Thank you.
Yeah, thanks, Guillaume. Unless you dropped in a couple of videos today, well, a videos on the section there. Is this something you could see that could be used for weir designs? We have a lot of weirs in Wales, Scotland, right across the UK, and a lot of problems with fish passage and barriers. So having a weir design with fish passes, eel passes on, dropped into a channel like this, being able to see the velocity distribution, kind of a model.
Yeah, so the main thing is here the idea is first to study the impact of these environmental error sources on the image-based measurement. And so Manteflow that we use is designed for computer graphics. So the concerns are a bit different than traditional CFD tools. So as we can see, the results looks really realistic, and that's the main concern of computer graphics. But the accuracy of the physical accuracy of the simulator is not guaranteed as traditional CFD tools. So I don't know if for such applications, it's exactly the good.
So yeah, it's really good visualization.
At least for visualization, but if you want to have physical, analysis, exactly, yeah.
Two people in the chat asked a question. So someone asked, were you able to compare the simulated runoff with the measured runoff? And then someone also asked, did you manage to compare the turbulence properties?
No, so turbulent properties, actually with Manteflow, I did not get anything about turbulence properties. So we cannot extract the turbulence properties. I mean, this is very basic. It's like you just set an inflow object, an inflow velocity, and then you have your particles and the mesh. And that's it. Then we extract the velocities, but I did not get anything from turbulence, and we did not have any interest in this turbulence. And what was the other question?
Were you able to compare the simulated runoff with the measured runoff?
The simulated, well, this is what I just showed, no? I don't really understand the question. So yeah, we simulate. So we compared actually the reference velocities that we have, so which are the simulated velocities, to measured velocities with LSPID.
Okay.
So that's what I showed. I don't understand the question.
Runoff meaning discharge.
Oh, discharge.
Yeah.
Sorry. No. So actually, we just focused on velocities, as it is the interest, and then the runoff, the discharge. It could be calculated as we know exactly the transect and we know the velocity distribution, so we can compute the transect. But the simulator does not give any information again about the discharge. So yeah, future work it could be, but actually the idea is just to focus on velocity.
All right, I think we have to save the rest of the questions for the break, which is the increasingly longer. So next, thank you. Next up is someone online.
Yes.
Subaki.
So they're doing a pre-recorded video, but they're in the call. So if anyone has any questions at the end, if you just come to the mic and ask, then they'll be able to answer.
Okay.
So I'll just get that up.
This,
yes. Oh yeah. Okay.
Working at Slava University, Japan. And today, I'd like to present the presentation entitled Optical Surface Velocity for Practical Use. flood observations, good flood and water resource management related to the SDGs and so on. Also, if we can prepare a very easy way to do optical flood observation, it can be used for the secondary or elementary educations. We can teach the rivers quantitatively. So how to provide easy to do optical surface velocimetry? Smartphone. Smartphone is developing its performance and function day by day. So that is one important product. Digital map, geographic data covering almost every area. So now our travel become very comfortable. Such renovation of the map, digitalizing the map is quite important components. For resolution survey, underwater topography, bathymetry can measure by using UAV or airplanes. So that is also third important innovation related to the topic. So device, service, and data. Three key factors. And device, service, data. Device, service, data. So combining three components. So there is an app is provided by the App Stores and the Google Play Stores free of charge. So let's see what can do by using this app. Using this app. This is the first screen downloaded the DEM. Now screen showing the camera image preview at the left-hand side and the DEM mesh overlay at the right-hand side. DEM has downloaded from the internet on the overlay to the camera image using the positioning sensor of the devices. So the camera of the device has directed to the river surface from the bridge. So we can see the topography above and below the water surface simultaneously. So real-time overlay of the DEM tells us a very clear picture about bathymetry, underwater topography. So we can see the right-hand side is deep and right-hand side is shallow from the right-hand side figures. Another demonstration of the app. So it's being also photos. But no problem. Using the smartphone while walking is not not good behavior, but maybe it's allowed for the scientific experiments. So working on the parking lot, the camera image is also rectified in the right-hand side on time and overlaid to the Google Maps satellite images. The portion matching is not perfect, but not so bad. The ground here has an undulation, and such undulation is not accounted for the auto rectification at this time. So that's one reason for providing the positional matching accuracy. But anyways, walking under changing the direction, and we can see the camera image left-hand side is well also rectified real time in the right-hand side. So this the direction always could also rectified. Now, sidetracking the topic, in this workshop, 2D and 3D electrification have mentioned. The 2D electrification indicates that DC beads are placed at the water level. 3D electrification, these beads are located above the water level, and the water level has accounted independently. However, the 3D electrification would be electrification accounting the three-dimensionality of the target surface. Our study does not account such an aspect, but maybe such a feature is important to treat high fluid number flow occurring during intense flood in steep slope rivers. Maybe it's good to call the second type as a quasi 3D electrification, but it's worthy, not a good idea. Now we go back to the LCD. This is an example of the on-time PID. So we can take in the video of the stream, and in the right-hand side, velocity at the 9 point is estimated real time. Let's try now. Actually, there's many problems, several problems demonstrated here best trial in the there is many several problems to be managed where to realize the optical surface velocimetry for everyone. I think there are three problems not solved and needed to be managed. First is the positioning accuracy is not enough. The second problem is no comprehensive EM covering the bathymetry. The third one is water level matters, water level for also electrifications. So let's see one by one. The first problem, positioning accuracy is not enough. Horizontal accuracy is acceptable, but the accuracy of the elevation is a matter. So accuracy is not enough for elevation, 2 meters or something. By obtaining ground elevation using the existing VM, as did in this project, is a solution to manage the elevations of the camera. So by using the elevation of the ground and the height of the camera relative to the ground is easily measured. So the camera elevation can be well obtained by using the DEM. RTKGS is provided very good accuracy for the elevation. So that is one ultimate solution for the position accuracy. I'm not sure we have a commercial available VRL RTK GPS included smartphone, but technically it's doable. The second problem, more comprehensive EM covering the bathymetry. So some substrate-based EM, for example, ALOS data contains bathymetric data. And sometimes such bathymetry is not bad, but accuracy may not enough and or not guaranteed. That limits our capability of the estimating the flow rate. For this project, a Untitled DM is prepared by myself only for the small test section of the radius. So let me know if there is some project storing the DM, including underwater elevation in a seamless manner, like map tile provided by Google Maps or the OpenStreetMaps covering almost worldwide. Like other here is a DM prepared by myself for this project. There's another problem related to EM. So morphological change is happening in some rivers, but how to manage the problem. maybe so common with the CFD model predicting the bathymetric change to revise the bathymetry day by day. Such technology to revise the change of the bathymetry. Third problem, water level mapping. So the laser range finder is easy to use, but not everybody has it in the field and not stable to detect water surface. Coupled with online real-time flood water level prediction model along rivers, maybe when ultimate solution to obtain water level everywhere safely. So message today toward practical use of optical surface velocimetry. Let us prepare an easy-to-use bathymetric database. If not, hopefully preparing the DM with internationally cooperative manner for seamless area cover, including developing countries. Such a database will be a good infrastructure for river or flood management, but also for public use. For example, using regional use. Water depth estimation based on water surface flow is a significant option, and I think one important topic discussed in this workshop, but it is better to have directly measured good quality bathymetric data. Thank you for hearing the presentation, and that's all.
Yeah, if anyone has any questions for Ryota, just come up to the mic. Yes.
Hi, Ryota. Thank you for the presentation. Just a question, something maybe I didn't understand. If you don't have a DEM, is it possible in the app to include just the bathymetry of a cross section that you have measured maybe with an ADCP or just with GPS? Or do you need to have this DEM to run the app?
Thank you for the question. So at this moment, the app only use the DEM data. So how to say, cross-sectional data is not able to directly use, but it's able to output only the velocity, surface velocity data, and then by using such data and combine the cross-sectional profile or bathymetry by using the PC. So it is, I think, manageable.
More questions? Yeah.
Thank you. I have just another question. We have seen in the screenshot that you have that for the LSPIV measurement, you only use like 3 by 3 integration areas. Is it possible to have a denser grid, like to make more velocities measurement?
Technically possible, but at this moment, we fix 3 by 3 9 velocity for simplify the how to say interface. How to say that scoring of the smartphone is quite small, so it is a trade-off. But technically, okay, doable. But at this moment, only the fixed point is used for the estimating the velocity. Thank you.
Thank you. So I think it's time to move on to the next presenter, which is Salvador. Please come up. Thank you again, Ryota.
Sorry.
So thank you. Good morning. It's a long title. I was thinking of an alternative title that could be how to still be able to get data when things don't go as planned. So next, please. So yesterday we were seeing the discharge app, and actually the same methods are implemented in fixed stations, like the one that we have on the right, where we have a camera and edge compute. These stations are the next one. They are measuring every 2 minutes, and we have installed like in different places. So they have these, some examples of how these fixed stations look like. So for example, here you see like the camera in some places is difficult to see. This is where actually we were talking during the breakfast. So from here to the other side is 700 meters, or just like smaller rivers. As I was saying, these fixed stations, they are measuring continuously, differently from the app. They also do continuous optical level detection, but we only have one camera. So our level detection relies on seeing, like in this case, the interface between the water and the shore, and to have a detailed bathymetry. In this case, for example, the water, we don't see the shore. The water came very, very close to the camera, but we were able to still measure because actually there is we are getting the data, the water level data from external sensor. So also we can connect different type of sensors to the station, and also output data. So what I'm going to show next, please, is a station that we have in the Emirates, is on the Wadi. So Wadi, they look like this. We have seen that like for 1.5 years, and suddenly comes the flood, 15 minutes, 3 hours, it's gone, and then they wait for the next year. So for 1 year, we've been measuring trucks. So normally the body is also used as a road. So this is poses different. Oh, so here is the camera. Probably you don't see it, but it's like 150 meters away from the other end. And so that poses some difficulties on setting the station on the site. And additionally, we did all this remotely. So fortunately, they were working at 49 degrees. So we were in the office. But it's very difficult to know and to have a picture when we see these images. We don't even know where the riverbed is. You know, it's very difficult to sample, very difficult to communicate where we need the ground control points. Just a bit complicated. Next one, please. Well, that's the picture of the camera. So this is the event that we had. So it's a different body from that picture. So we have different bodies. And the problem is that, as I was mentioning, the water level came out or the shore disappeared from the image. So we were not able to measure the water level. So this is this image here is at this point, and the next measurement that we had was at this point, and this is 12 minutes in between. So it went from 5 cumex to 205. So that is 12 minutes, and from there on, so we lost the level. So we cannot calculate the wetted area, we cannot get the discharge. But we were able to measure the surface velocity the whole time. But so the question here was, okay, what can we do with this data? So can we still be able to reconstruct, at least as a proxy? We know that it's not an accurate discharge measurement, but so we have some data. What can we do with that data? Meaning surface velocity that we have. Next one, please. And as we know, and actually it was quite interesting, we have several talks in this workshop about what we can see on the surface reflects what we have in the bottom. So actually here is another station that we run continuously. And this is the surface velocity distribution at the same level at different times. So we see that the surface velocity distribution is changing over time. That's an indication that the cross-section is changing. So actually also does give us the option to measure the surface. When we gather so much data, like every 2 minutes, we can do more probabilistic discharge measurements. So we know that we can learn something out from what we see in the surface. No? So what we try to do is to relate the surface velocities that we kept measuring to the discharge. No? So we plot them, we made a very coarse fit, and we use the surface velocity to infer what was the discharge during that event. So we measure up to here, and then this is extrapolated. So there, as again, this is just an approximation. Actually, the surface velocities so we need to measure in the orthorectified image. For that, we need the water level. So we orthorectified at the latest highest water level that we measure, and we keep there. So already there is an error because we didn't correct orthorectification by different levels. Next one. And then we keep going, oh, so can we get the water level? So we try to do the same, just to try to fill the missing data just by trying to make a fit, very rough manual fit. So between the surface velocity and the water level. So here is the start of the event. Here is those 12 minutes that jump up to here, And then this is what we try to fit roughly by eye. And then the event that then comes down, we have it again on the image and comes down. And the point was additional problem. Never came back to the same point. And if we measure here, it's approximately 70 centimeters. And when the water level comes, or we see the shore again on the image, we can start keeping measuring again the water level, you know, because now it's again back on the image. And again, never came back to the same point. And we see again the 70 centimeters difference. Next one. But because we have the images, so this was before the event. Which one, please? And this is after the event. Also, we see that in 5 hours was 70 centimeters of sediments on the riverbed. Next one. So very difficult case because we still try to reconstruct the hydrographs for that event, but was difficult to. So there's another source for the rectification, and that during the event, the cross-section, the area was changing, so which also was not considered. We assume that most of the sediment or the sedimentation happened at the end, so it was very, very fast, and then probably was sedimented later. So the errors on the discharge probably could come back later. We could work this in a more iterative way. Now we have the height. We could run it again to do rectification and to try to do it a bit more, iterative way to try to improve a bit those data. But again, it was like, okay, we have surface velocity. What can we do with that? And so we just try to get a process of the discharge. I think that's it.
Thank you, Salvador. Do you have any questions online or in the room?
No, I never done it.
Salvador, did you actually manage to quantify the channel area changes and that's certainly is the position that sediment being in one area?
Yeah.
So yeah, what's the percentage change? So
No. The thing is that we always trying to sell stereo cameras, not stereo cameras, but we have the solution to put 2 cameras and actually like those type of cameras, but wide apart, not like 4 meters. So we can be flexible to reconstruct, but it's very difficult to convince people that they mount a different camera. So just with 1 camera is not. We just have the position. So those 70 centimeters what we measure at the far end of from that wall. And to really reconstruct it, we need that.
but no one actually surveyed
No, so now, so that's the idea also to do this like this probabilistic or doing every 2 minutes, because we see when the surface velocity start deviating for the most probable value, is the indication that okay, someone has to run out of the field. So that one they surveyed again. We have to change the dosage.
Alex? Very technical question. What is the lifetime of camera at 50 degrees every day?
Oh, so that been not exactly that. The first, so there were two bodies, but I showed the pictures of the bin and the one at the end. The one at the end actually is quite recent, but the first one is in I guess it's 1 year, 9 months running, and still there. And I guess also the problem is the lost fire. I guess so. The breeze, the lost. It's quite rough environment. We will see how many more months.
And you compare it due to this high temperature, like the optical parameters maybe changed or something, you know, like is the field of view always exactly the same between the first installation and now?
Yeah, actually, not, but it's easy to check. We have the point where we will try to run the calibration again exactly the same to see the construct level. But no.
I had another question, just on one graph you showed. You analyze the surface velocities for the same height and compare them.
Can you go back to that one?
Yeah. So I was wondering also if these variations are, they can be due to the cross section, but maybe also if you, I don't know if you have the error, like if it can be due also to the optical measurement itself, you know?
Yeah, so that's can you go all the way to the end?
Oh, sorry.
No. So just keep going. There are some extra slides. Next one. So this is like a single measurement, no? And then we take this error because that's our feed. But actually, that the image that you saw before is not showing this error. So we only take the feed.
Yeah.
And the variation of that feed. So we are assuming that this scatter is more or less constant. So we have the same measurement error, but accumulating. So in one of those graphs, this animation, some of them they are taking 2,000 videos. So I guess so. It's and what we are plotting is this blue line, and that over 2,000 measurements and how it is changing.
Just related to that point, Mark had some interesting data the other day at the rising stage and falling stage. Do you think some of that variability in your cultural distribution?
Yeah, also could be. And actually, it's also that one. Actually, here is, I mean, I can see if we could have a bit more, I would see it here, no, also the rising. I mean, never came back here, no. But those are so it's measured, right? It's getting that, but we can see the rising. Again, it's a bit of imagination, right? Because I don't have these points here, but I will guess it went like.
Yeah, I guess I was thinking that the figure where you've taken velocity across the channel at the same time.
Oh, those ones, yeah, right. They're filtered. So we are taking the same. So actually, this is quite an interesting case because it's a hydropower. So they have daily cycles. So that's why we could gather many data for different levels. And so we take only the right racing ones. Yeah.
Thank you so much. Actually ended the session before time. Much to my amazement. So yeah, I suggest we'll go for coffee, and I would like to talk to the people who are doing discharge measurements yesterday, because we need to substitute Nick. Yeah.
I think you can take some time to, that you can present the result of this stereo.
Yes.
And then just deliver the result.
Michael, would you like to chair that session? I mean, read the sheet.
No, what's the sheet for? I don't have the data. You can see just like. Yeah. It's not combined. Yeah.
The next session, we chair by James. So then the last one, which is analysis the dates so you can be, you can share. Then you share.
Just a session after lunch. Yeah. It was just a session.
Yeah, because the next one, James, yeah, which is the last. When we have a sign and the results for the that's the series for the kid. Just yeah, was good and
The result you get for the some results.
yeah, exactly.
The order results you get on the different. Why
But it's supposed to be fun and it's flexible session.
Yeah, that's it.
We're all friends.
Okay. Okay, guys, this is the test.
Yeah.
Yeah, because you have to change the settings. When I speak, it goes right in.
That's like 100%.
This is the test. Again. This is the test again. This is the test.
Erica?
Yes, can you hear me?
Yes, yeah, we can. Is everyone ready for the next presenter to start?
Yeah.
Yeah.
So yeah, if we can make a start. So this is session 5 about development. So our first speaker is going to be online. So that's going to be Erica Johnson. So I'll hand over to Erica.
Okay, can everyone hear me and see the slides, both online and in the room? Good, okay.
Yes.
Okay, awesome. So to start, I'm sure some of you will recall from last year's Surface Velocimetry Workshop that my whole research focus is the inversion problem. It's basically taking pictures of the water surface and backing out important hydrological parameters. And in that workshop, I presented 4 different techniques for remotely measuring such flow parameters such as the flow depth, the volumetric flow rate, the bed shear stress, and the vertical flow structure. All of these techniques relied heavily on remote measurements of the turbulent velocity fields. They're very much based in turbulence. And measuring the turbulence velocity field in the laboratory is a relatively easy thing to do. This is a schematic of the channel and a picture of the channel in which I conducted all of the experiments to collect the data to develop those techniques. This channel is located at DeFries Hydraulic Laboratory at Cornell University, where I did my PhD with Todd Cowan, who is going to be delivering the keynote in a little bit, in about an hour or so. In the laboratory setting, it's fairly easy to control the seed and the illumination conditions, making remote measurements of the turbulent velocity field, as I said, relatively easy to it's relatively easy to make those measurements in the laboratory. However, if I want to start applying some of the techniques I've developed in a field type setting, I need a robust method of measuring turbulence velocities in the field. And this has been the focus of my research program currently. Now, the types of environments I'm interested in working in. I'm working in nearshore coastal environments as well as riverine environments where there are surface waves that are present on the free surface. And so whatever sort of current velocity technique I use, it needs to either leverage the presence of waves in the technique or not be adversely affected by the presence of the waves. The environments that I'm looking at are on the order of 1 square kilometer or typically less, but sometimes more than that. And so when we're dealing with such large environments, trying to seed them becomes just impractical. Like the sheer volume of seeding material that I would need in order to see these environments such to get really well resolved and accurate turbulence measurements is just prohibitive. It's just not practical to do. So LSPIV is not necessarily the best technique for me moving forward. At the time that I began this research program, I didn't have access to one of those fancy IR camera that Seth presented in his work. However, I currently have access to 2. And so moving forward, it will be interesting to kind of compare the IR measurements with the technique that I'm going to be presenting today. And certainly working in the field, since to the best of my knowledge, none of us controls the sun or the atmosphere, we have to deal with variable lighting conditions in the wind, and any technique that I would use would have to be adaptable to those sorts of variations in the environmental conditions. So I started off looking at these power spectral density techniques, and this is what Julio presented. I think that's how you pronounce his name. What he presented on Monday was basically what I'm referring to as the 3D power spectral density technique, which basically uses a cube of images, a stack of images in time, and we do a 3D FFT both in space and in time of the stack of image cubes that you can see here. And in Fourier space, the output of that 3D FFT is this classic cone-shaped dispersion surface that you can see here. When there's no current present, this surface is perfectly symmetric about the origin. However, if there is current, the waves are Doppler shifted and this dispersion surface tilts in the direction of the current. And the difference between the zero current and the Doppler shifted current surfaces, you can back out the velocity. And this technique is very proven, it's very robust, it's been around for decades. And however, because you have to, according to what I've seen in the literature, this technique requires on the order of hundreds of images to adequately resolve this dispersion surface. So for someone who's interested in high temporal resolution turbulence high resolution turbulence measurements, this is not necessarily the best technique for me to use. So I went digging through the literature and I came across this 2D power spectral density technique that was originally applied to satellite images of the ocean surface. And if you think about it, as a satellite is falling over the scene, it may only capture 2 or 3 images, or sometimes 10, but a very relatively smaller number of images. And so they needed a method to back out the currents in those types of situations with very few images. And so I saw this technique and I was like, hey, I think this is going to work really well for our application. So the way this technique works is I have these are sub windows from images of the wavy surface, and the images are separated by some small delta t. I take the 2D FFT of these images, and the output of the 2D FFT is there's two different outputs. There's a real part of the output and the imaginary part of the output. The real part measures the spectral energy as a function of wave number. It's called the cross spectrum. However, it's the imaginary part that we are most interested in. The imaginary part is called the cross-spectral phase. It is basically quantifying the phase shift of the waves between these two images that are separated by a small delta t. So I can take this cross-spectral phase, and if I divide the cross-spectral phase by the wave number and this delta t, I can cast that phase shift in terms of the phase velocity. And you will see why I do this in the next couple slides. So I'm going to take a quick digression to talk about the dispersion relationship. Okay, so the dispersion relationship describes the relationship between the wave number and the angular frequency. And what we see that, that we have this relationship, and when there is a current present, the measured frequency of the waves is Doppler shifted, it's increased. It's not necessarily equal to this theoretical relationship here. So when we have a current, the waves are Doppler shifted, it changes the observed frequency that we see, which is this omega. So if I have the wave number of the images and I can measure this wave frequency here in the field, then I can back out, I have a method of backing out the currents. So in all of the situations that I'm working in, the waves are, I'm having some problems advancing my slides, okay. The waves are shorter than the flow depth. So this hyperbolic tangent term goes away, simplifies the dispersion relationship, and I take this relationship and I recast it in terms of the phase velocity by dividing by this wave number here. So I end up with this expression here, where if I have the measured phase speed, if I can measure that, and I know this theoretical wave speed, that's just gravity divided by the wave number, and this is a known quantity, I have an expression for coming up with the current velocity. Okay, so coming back to this slide, I take my cross-spectral phase, cast it in terms of the phase velocity. I can plug that in here. I know my wave number. I have a method for measuring the current speed. I don't know, there's just not, okay, here we go. So just to give this to you pictorially, here's the cross-spectral phase again. You've seen this, and when I take this image or matrix and subtract the theoretical phase speed, again, this is just gravity divided by the wave number, I end up with the velocity distribution in wave number space. And this is very powerful information, and I can leverage it in a number of different ways. Certainly, I can apply some sort of averaging technique to map out the velocity field in the scene. I can also leverage the Stewart and Joy approximation to map out subsurface velocity profiles. And this technique, this approximation basically says if I have a wave of a certain wavelength, that wave contributes to the velocity field below the free surface at an amount that's equal to half of its wavelength. And so this is basically just a one-to-one mapping. I can map out subsurface velocity profiles. And one thing that I noticed was that if I can average this velocity distribution of wave number space, I can average over all of Kx and all of Ky to come up with the velocity spectra. Now, this is something that I'm still working on, but I do believe that this is the velocity spectra that we're used to seeing in a more traditional laboratory setting. As you can see here, there's the -5/3. We've got -5/3, the spectral turbulence cascade that we're very used to, and also the -1 power law that we're seeing that when I average these spectra over all of Kx and Ky. And because this technique leverages only requires 2 images, I can start to look at time series information if I've got a whole movie's worth of data. And I can look at how the flow field is evolving in time. And so we'll look at a couple of examples. I'm using stationary drone imagery that was made freely available by Stresser et al. That was taken over the Elbe River in Lauenburg, Germany. Basically, the drone hovered for about a minute over this region of the river right here. This is the main river, and we have this canal section. So I've got about a minute's worth of data here. And when we start to look at the results, when I apply the 2D PSD technique to this drone imagery, there was also in situ ADCP measurements against which I can compare. I mean, you can see that the 2D PSD algorithm compares quite favorably to the ADCP results. You can see that in the river, there's much higher velocity than in the canal. And because these two bodies are kind of moving against each other, we're going to get some enhanced shear here, which you'll see in the next slide. If you look very closely, there's sort of a recirculation jet as the water comes down. There's a little bit of a recirculation here, and also a smaller vortice, both of which the 2D PSD algorithm is picking up on. So I'm able to, with my whole field velocity results, I can start to look at derivative quantities, and you can see that there's enhanced shear at the interface between the river and the canal, and also enhanced vorticity along that interface. And you can see right in the region where there is that very faint vortex, you can see there's also enhanced vorticity there. And so we can start to look at how this recirculation jet is interacting with the main section of the river when we look at the time series of, or how the velocity field is evolving in time. And what you can see is that there's eddies here in this recirculation jet that are kind of coming up and then entering into the main body of the river, and you can watch that evolve in time. And I can also, since I have about a minute's worth of data and about 154 images to work with altogether, I'm starting to look at, I guess, fluctuating statistics. And I will say in this technique, the wave orbital velocity is still present when I start to look at the fluctuations about the mean. I have not yet taken the step to separate that out, although that work is ongoing. So what you see here, these results are still informative. Here at the intersection between the river and the canal, there's enhanced fluctuations, which is exactly what you would expect here. And then I also have, we're going to look at 4 different points for the time series in the spectra. I've taken 2 points in the main river and 1 in this recirculating jet and 1 in the vortex. And you can start to see, and because this technique relies on 2 separate images, and I've got a whole video's worth of data, I can start to look at time series of how the velocity profile is changing. And I can also look at the velocity spectra at these 2 different locations. I'm not sure how much time I have left, but I will say that, in examining these spectra, they are exhibiting the types of trends that I would expect to see. Especially, in the river, that we have the streamwise velocity spectra that's slightly greater than a span-wise, which is what you would expect here, and the vortice that they're about the same magnitude. So we're seeing the right trends with these results. And I can also look at subsurface velocity profiles. Here, what you'll notice is that during the data collection, there was a slight increase in there was a slight wind that was present, which is affecting the free surface. And you can see that here. This is the velocity magnitude and this is direction. You can see that the influence of wind in these profiles, but then once the wind, once the effect of the wind goes away, that the profiles are fairly constant. Here we're looking at approximately 25 centimeters below the free surface. And so that is as far as we've gotten thus far. So certainly I'm pleased with our ability to measure the mean velocity field, but as I said, I'm interested in measuring the turbulence. And so in the future, there are a number of ways to decouple the wave field and the turbulence field. And so what we're going to be doing in this coming March is we're going to be flying some polarimetric cameras to try and quantify what the wave field is doing in an effort to decouple both the waves and the turbulent measurements. And so hopefully if there's a surface velocimetry workshop next year, I'll be able to present those results. Thank you for your time, and I'm happy to answer any questions you might have.
Can I ask a question?
Sure.
Yeah, okay. Well, actually, a couple of questions. So one is from what you just said. You try to reconstruct the turbulent velocity based on the surface behavior, but the theory used for the surface behavior for the waves is based on a flow without turbulence. So I wonder, how do you make sure that the surface responds within the time scale of turbulence, which can be much shorter than the one of the actual surface fluctuations?
So I'm not sure if I understand your question, but our approach is going to be to quantify the wave heights and then to relate the wave orbital velocity to that wave height. And then from there, we'll be able to separate the two out.
No,
Does that
okay.
answer,
No, yeah, sorry. Maybe I wasn't clear. So the velocity fluctuations you're showing here,
yes,
those are based on how the wave velocity is shifted by changes in the underlying flow velocity. Is that correct?
can you repeat that?
So when you reconstruct these velocities, this would be the velocity of the flow, which is affecting the waves in a way as you recover, right? But that would not necessarily represent turbulence. Like there could be lots of shorter scale, smaller scale turbulent fluctuations, which perhaps you wouldn't be able to group. So that the wave dispersion relation is based on the idea that the flow is homogeneous. So it wouldn't really include turbulence in the way it is defined.
Okay, I would argue that, I mean, certainly the small scale turbulence, I'm not going to be able to get given the size of the sub windows, that sort of thing. But I'm primarily interested in, I guess, the larger scale turbulence. And I would argue that I do believe that I'm getting that based on the presence of, I can see vortices. And I can watch them evac. So I do believe that I'm getting the larger scale turbulence. And that's really all that I feel like I need.
Okay.
For the techniques that I'm going to be applying.
Okay, if I can ask another question, I don't know if somebody else has some. So it's very nice, and I really like it because it's something that I have been trying to do in the past and I failed miserably. So I wonder how you manage, because one of the reasons why I kept failing is because this method assumes that there is a one-to-one correspondence between frequency and wave number. But if you have some surface structures generated by turbulence, for example, they could have the same wave number, but they will have a different frequency and a different phase shift from the gravity waves.
Yes.
So did you have the same issue? How did you solve it?
So I don't think that I have that particular issue. I think that, let me see, how do I put this? I think that because so I'm very confident in our mean results. And, definitely still working on getting to the turbulence. I don't think that a minute is going to be long enough to resolve the mean such that I can get the turbulence quite correct. I'm not sure if I'm really answering your question though. I think in order to, I mean, so we're going to be relying on basically constructing what the wave field looks like and what the wave heights are to separate out those two. So I'll have, you know, some sort of measurement, and then I'll have what the wave field is, and then I'll basically apply a linear assumption to separate those two out.
Okay, thanks for that interesting discussion. We'll probably have to
Okay.
end that there, and perhaps it's an opportunity for you to take that offline.
Yeah.
Change contact details between you two if you wish to continue that discussion. I just want to make sure whether in the room here at Lancaster, whether there's any questions. Yes, if we could just have one, that'd be great.
Yeah, just one short question.
Hi, Erika.
Hello?
Just one question, maybe something I don't understand. Will your method and the quality of your method be affected if you have visible patterns, like not only waves, but like foams or floating debris on the images?
That is something that I am, you know, currently looking at. Certainly, I have a PIV type code embedded in this one that they work. I'm basically doing both at the same time, so I can kind of look and compare. It definitely does show up. And the way that I would handle that is to, I mean, you can't necessarily use the dispersion relationship if you have something embecting out, but I can, you know, kind of flag those sub windows and say, okay, for these sub windows, we've got a lot of, you know, stuff embecting through. Let's switch to the PIV version and then kind of map those two out together.
Yeah, okay, thank you.
Many thanks, Erica. Okay, I think we're going to now move on to the next speaker. So our next speaker is John Hyde.
Giving away my first slide. So talk about something a little bit different now. When I like to give a presentation, I don't like to put lots of words, and I'm not putting many equations, but this is actually built on a lot of equations and a lot of mathematical work. So I like to show some pictures. I work that way. So I'm going to talk about flow on the go, and I'm going to start from a university style presentation and transition into our spin out style background, and you'll see all the commercial talk and a big demo at the end. So this is our smartphone and web browser optical flow tracking velocimetry, or optical flow velocimetry. Depends which paper you read, because we once had a typo and we've got OFE and OFTV. So thanks, Will, for that. So I'm going to start. I always start a lecture by giving a historical background about someone who really inspires me. And I'm going to start with this guy, because I think for what we're all doing is he is the most important. And actually, like all scientific people, there's a book written about him, and it's this one, which is the Acoustics Handbook. And that's effectively what we're all doing, right? We're just tracking something, exactly what Winnie the Pooh was doing all those years ago. So let's start with maybe the background of what I'm doing with optical flow. So I'm going to draw a river. Apologies, my artwork's not the best. And let's just think about tracking a stick like this. It does shrink without my transitions. Okay, we've thrown our stick into the river. I tried drawing the bridge. And we can see that we've got this stick which is moving, right? So this always kind of messes with people's minds, especially if you've not seen a film before, and that's something more light or more common now, because you can see a film that's made of lots of images. So first of all, let's think of what a video is. A video is a set of images. So we've got one image with our stick, and we've got a second image, which is our next one. So we'll start with our first method that we all hear of, especially great for sticks, is particle tracking velocimetry. Many ways of doing this, very domain. You can go through physically, and I can say, well, that's moved to there. So I'm going to select this one, and it's moved to there. So that means that we've got a displacement. Dead easy, many ways of doing it, whatever way you want to do it. So that one's all right, but it doesn't always work for what we're trying to do when we're tracking rivers. usually we've got something like this. So we've got some features on top. So often we'll say, right, let's go to particle image first. So in a very simplistic way, we have two images slightly changing between the two. And we might say, well, let's grid it. So let's stick on some sort of grid. It might be adaptive, it might be moving, it might be circular if you love it on. But you've got this grid, and I'm now going to stick it into some domain. Fourier domain is quite useful. Do a fast Fourier transform, and I can find that point. I'm going to find how it's displaced. That's particle image velocimetry in a nutshell. There's a big book by Joe Festival. I'm sure he can explain a lot more better than what I can. So the next one is optical flow tracking velocimetry. So how does this work? Well, this is more about looking at features, and it's formed on this beautiful set of linear equations. And I like linear equations because you can simplify them using singular body decomposition. And it means that you can simplify them and make them really fast and really lightweight. And that's what we've been doing with this optical flow tracking velocimetry. So basically, we choose some points. We do this through an eigen method. We could do it through the feature tracking method, pretty much whatever you want. And then we see them in the next frame, and we just apply this nice linear transform, and we get this huge lot of velocity, this velocity field of points, and it's extremely rapid and extremely lightweight. Again, there's a lot more that goes into that, and I'm not going to go into it today. So what does that mean? So a few years ago, I was discussing this with a colleague, Andy Plater. This video is not working very well, and he's into waves. And he was saying, can we track waves with it? And I said, well, let's give it a go. And I mocked this up. Yeah, the video's not showing as well as I wanted it to. But this got us our first grant, which led to Wave Tracker, then Flow Tracker. And then that finally led to Flow on the Go, which is our app, and also web-based TV. So I'm going to play a video, and you might have seen this video because I actually spammed Twitter with it for quite a long time. So I got £10,000 from Innovate UK to do it. So I'm going to play it because it explains what we've been doing. So off we go. It's not got the sound. So Liverpool, by the way. How's Liverpool? Scary how many times I've seen that video. But what we can do is we can actually now take some. We can now begin to take any image and we can track it. So as you've seen here, we've got waves, and we can do this in a really lightweight form. And that's led to our mobile. So the first question always people ask is, how good is it? And we've seen that today about validation. So I've done some validation. Actually, we've published probably 10 plus papers in all different fields, from blast and explosions to, if anyone's here from the NA, went back to have your teeth scaled after COVID. Actually, Flow on the Go was used with the NHS to get us told off by the dentist having our teeth scaled. So first of all, I set out a simple problem, just a MATLAB-based code, to see how well it reacts. Put it in the app, tracked it. That's going to be, now I know exactly what the answers are going to be, so I can work that out. Can do our standard methods of error, and we can find, we can find out what our errors are. They're about the same if we apply our actual benchmark method, our Flow on the Go, and we've used some PIV method, which is just the PIV lab. We can see we're getting pretty much the same flow field. But again, this is kind of stochastic, so it's not going to be perfect. We could even stick some lines on here and start to see how they kind of match up. And we're seeing from the benchmark to the reality, it's pretty darn similar. We're getting in the right ballpark. So that's a simplistic way of looking at it. Next, we can look at how this is distributed. So often people are wondering about how these velocity distributions fit. So again, PIV is kind of under predicting, and we've got this Flow on the Go, which is fitting quite well to the benchmark. Okay. So it's looking quite good for that idealistic case. So the next is we go to the SPS PIV challenge, which was from the early 2000s, where they set out these challenges to see how good your codes are. And you're not seeing this PIV move really smoothly like I'm seeing on this screen, but we can apply Flow on the Go to this. It tracks really well. Still done in real time, by the way, so that's PIV working on your smartphone. Again, we can get some statistics from that. What does it look like? Okay, we don't have the actual results for this because this was some experimental work, but we can compare Flow on the Go to PIV. And we get some pretty nice results. Okay, a few extra outliers on PIV, they might mean something, might not mean something. Maybe a little bit smoother here from this optical photon. So at this point, I'm quite comfortable that for the lab scale stuff, it's quite nice. Distributions of velocity, and then I'll go to some videos that Mark sent me like 2 years ago now, something like that. And this is our ADCP across here, a river, and again, we gave it a go with flow on the go. It's true. And you can see we can track that quite well, and we see the speeds, and you basically expect that velocity distribution. Put that up, compare against PIV, and we're getting pretty similar. If not, we're actually getting a little higher resolution here with flow on the go. We're seeing a few extra points. We're seeing more some features that you might see. So this is quite neat. And this is all the stuff during COVID, during my travel grant, where I went as far as the gate to go and sell this, that I spent time going over and over this. So again, velocity distributions in the right ballpark, but you're comparing, you know, apples and oranges as such with an ADCP and surface flow velocimetry techniques. So that's it for me talking. I'm going to show you how it works. So I'm going to switch over now to a demo, and I'm hoping this is going to work quite well. So I'm going to start by showing you the app, and then I'm going to show you some new technology. I did promise at the end of this talk that we'll be releasing this today. That's not worked. It's going to be, I'm going to say the 1st of October. I'm going to say that, and that's the deadline I'm giving them now, the 1st of October. So if you just give me a second while I move over. I'm just going to swap screens. Right, so this is it. So this should be my phone now. I've spoiled it a little bit by jumping straight in. So we've been working on this a little bit, and actually, one of these things that has slowed us down a little bit is GDPR, because we want to actually be able to get you in here, log in, look at your videos. So we can log in. So I'm just going to pretend I've logged in. Okay. So we enter into this flow on the go screen. We've tried all sorts with capturing videos. So you can capture a video in there. So we did some of that yesterday. So we can go on here and we can open up the app. It's working a bit faster on here. So let's start with maybe a video that I just captured yesterday. You can click process. Okay, it's going to be crazy because it's chosen loads and loads of vectors, but it's going to be a bit adaptive now. And it's going to start saying, well, I found all this moving, so I'm going to be able to track it. So we can do a few pre-processing techniques here. So I'm actually now going to take some of the drone data we looked at yesterday. What we've got, that one is just here. And it's a rather large video. It's 200 megabytes that's just read in. And this is some of the stuff that Mark took yesterday. And we can say, right, well, we're going to put scale on this as well. So, okay, this is right over the top. So I'm going to say our distance, I know, was 10 meters between our 2 points. And I'm then also going to say, well, let's choose those different distance points, which was between here and was between here. So there should be 2 lines. Let's just put that in there. So I can do process. And that's it. So we're now tracking with PIV, or with OFTV. So we've got these velocity distributions. Pretty good. Okay, well, this is neat, but you can't do statistics as well to that. Well, you can do some Lagrangian statistics if you want to look at the life mass exponent and look at that, how it moves into chaotic motion. You could do that, but maybe not what we're going to look at in a river. So let's just trim this video down a little bit. So I'm not here all day. Just choose a small time, the process. It's going to process this. So you might be in the field and you might think, right, well, I want to do a few statistics on this. I might want to look at some of the gridded velocities. So there's a few thousand images. I'll just let this go through a little further. Okay, so we've got some velocity fields here, just processing this small time. And now I'm going to say, well, I actually want to look at that as a gridded velocity. So we can now see what that would look like as a gridded velocity. So that's almost instantaneous PID. Yep, no problem. Jim. So we can zoom through, and we might also want to say, well, what's the mean velocity? So we're looking at the velocity magnitude. And we can see we've got velocity magnitude and we're about 0.5 meters per second. And that's what we're all getting today. So that's just from on my phone, can send that. We can do some really neat stuff. We can also do some other neat stuff, which I can show you later, where we can track waves. We can go and point this at waves, and we've got a frequency spectrum in there, so I can give you the amount of waves which happen, which is quite neat to see how good students are at counting waves. I'm just going to show you one last quick thing, which I'm quite excited about, if that's okay, which is now what we can do within the browser. I told this is lightweight, that's written in C, but what happens if we write it in a language like JavaScript, which we can do? So we can stop sharing the screen. This is why we shouldn't do live. Okay, so this is going to launch in a few weeks. So it's a drag and drop version of Go on the Go Online. It's all written in JavaScript. And if you've ever written in JavaScript, it's a painful language to write in. And had some help with Michael, PhD student who's done some really good work on this. You can export your video straight from the app onto the browser. Oh, look, I've got that video there, which has come straight through. We've also got this video. We're going to use this video. It goes straight in. And now, using just the browser, okay, it's now going to do exactly the same tracking. Okay, the color bar's not working. A bit of illness last week, but we can do all of the tracking in the browser. It's as lightweight as anything. This is the same thing as what you've just seen on the phone. It's there. You can download it into a bin file. You can then go and play in MATLAB, and you can actually do some statistics. So yesterday I done some statistics. We put it into the next session. So I've got the turbulence intensities, I've done kinetic energy, all from that video that we've just seen now. So that's Go on the Go. Question.
Okay, so if I can invite questions from here in Lancaster first, please. Yeah, please go ahead.
You have the velocities.
Yeah.
You have anything to Discharge.
I've always said this about many times. It's okay, it's not perfect. I've got surface velocimetry, times it by 0.8, times it by the width, and times it by about the depth, and you get the discharge. Yeah. So no, I didn't want to include it, to be honest. I didn't really see the need for it. I want to keep it as simple as possible. So, you know, it's all the way from lab scale. We can go and do some PIV, quick point it there, and it's a laser current all the way up to a river. We're doing some structural collapse with it. We've done blasting explosions with it. Done all sorts of things with it because it's just something which is lightweight. So,
And the question is, because after that, can you compute the discharge for this afternoon so that we can compare with something?
yeah, no problem. Yeah, of course, that's velocimetry.
Jane, it looks very cool.
Yeah.
Something on the beginning of the models.
Yeah.
Of physics. That's cool that in light what we've seen already.
Yeah.
In SPID.
Yep. This is using optical flow, so it's slightly different. So instead of actually solving a Fourier-based problem, you're now taking this into a linear algebra-based problem. So you've got a direct solution, and I find it's like one of these unformed set of equations which are really, really nice. As we were talking about yesterday with your problem with the microphones, you almost end up with that square matrix problem where you can then start to be quite neat with that and be then optimal on how you then process things. So you can cut the equations down, filter things out. So that's how it can work on the phone and on the browser. Yeah.
How do you interpolate the values where there is no, calculated velocity?
So there's ways of doing it. That's just it's a histogram effectively. So if you wanted to be more clever, there's algorithms we can do. There's a bottom filter we've written previously that would do it. But for this, it's just as bit the basics of what we can get from it. That's given us a discharge, it's given us a number.
Okay, is there any questions online?
No.
Okay,
Okay.
good. We'll be ready soon. I'll let you all know when it is ready.
Yeah.
Okay. Thanks.
Well, I believe our next speaker is online. It should be James Van Hoff. Is that correct? Yeah. James, are you there?
He's on.
If you could try again, James, can you hear us okay? Send me a message by chat.
Yeah, I'm just, he can hear us, but yeah, we can't hear you, James.
Volume.
Yeah, volume stays the same.
Yeah.
So what if you could just.
Can you talk now, James? Not be bad. I don't think it's. I think it is. I mean, it hasn't been. Well, wasn't it terrible? Yeah, but not. Oh, he did.
So we can't get his microphone working, so we're just going to ask if Edwin can bring his talk forward and his keynote forward by 2 minutes.
Yeah, I think we think it's David's.
Yeah, it's not a problem. Yeah.
Can you hear me now?
Oh, yeah.
Oh, you can? Okay, I'm very sorry about this technical glitch. Okay.
Okay, James, if you're ready, we'll hand over to you and you can start. There we go. We can see your presentation. So over to you, James. Thank you.
Okay, perfect. Sorry about that. First off, so yeah, my name is James Baumhoff. Thanks for organizing this in-person and virtual conference. As you've just seen, obviously there's technical glitches that need to be worked through, and I appreciate being able to attend virtually. So today I'm with the Water Survey of Canada, and today I'll be presenting on image velocimetry using mobile cameras within the Water Survey. This project is led by myself and Elizabeth Jameson, my colleague, who was at the Nordic workshop last week, so you may have met her if you didn't know her already. This is a 5-year project. It's one of many projects where we're investigating new technologies for use in operations. Those include dual water sensors, radars, database upgrades, etc. And for this project, the objectives are first, assess the suitability, accuracy, and feasibility of image velocimetry as a non-contact discharge measurement technique for a variety of streamflow conditions at existing hydrometric stations. And then secondly, determine if, how, and where image velocimetry could be used within water survey operations. So yeah, this presentation is largely from an operational perspective. And for an outline of the presentation, first I'll give potential uses that we see in operations, talk about how we're gathering measurements, and then I'm just going to go through some use cases of where it works, where wind causes issues, and then different angles and how that affects ultimately the discharge, how I've seen that, and kind of throw some questions out there for that I'm hoping people can help with, and then finally some conclusions. Okay, so potential applications for water survey. First is backwater. Often in the springtime, you'll get ice jams, and that'll cause backwater, and that'll cause your stage discharge curve to basically not work. And so image velocimetry has a lot of potential use there. And then water survey has over 2,000 gauging sites across the country. A lot of these are remote, hundreds if not thousands of kilometers to get to. And if they're not remote, sometimes they're really flashy and you just can't get to them in time to get the high flows. And then rapid curve development is another potential application we see where you can just get measurement after measurement very quickly with image velocimetry, and we've seen examples of that already. And then finally, and this is particular to mobile measurements, is rapid and safe measurement. We've already seen examples where you just can't stick a boat in the water, and that's where getting images and videos for discharge measurement make a lot of sense. We are doing fixed camera image velocimetry. Liz presented on that last week. And so if you weren't there, we can send you the presentation. And this is just focusing on mobile measurements. Okay, so how are we collecting the videos? We've got a fleet of 7 Mavic Mini drones. We like the Mavic Minis because they're cheap. They're about $500 Canadian. They're small. You can throw it in a backpack. They're effective. They have 4K video, and they're under 250 grams. And so the drone regulation is evolving in Canada, as I'm sure it is everywhere. And under 250 grams, it just means the standards are a bit less rigorous. And so as we kind of figure out how to fly these safely within operations, it certainly gives a bit of peace of mind for that. So we've also created, we have a process for flight logs. This is just a front page of an example of someone who's flown the drone, what kind of information we capture. It's about a 4-page document that I didn't show here. And then we've created standards. So when a tech goes into the field, they fill out this form, and it helps to make sure that one, they understand what they're doing, and then 2, they're capturing critical information. It's easy to not capture a control point necessarily or mark where it is, because the tech isn't necessarily the one who's processing the measurement, at least at this time. And even simple things like, what bank did you start on for your cross section? Left bank or right bank? Those things sometimes get missed. And for control points, we're either using survey level rods for NADAR views, and we've also found it to work quite well. We've got GPSs for our ADCPs, and we can adapt those just to do our RTK surveying with those with those GPSs. So it's been a cost-effective way to use equipment that we've already got. And then to date, so we've captured 37 measurements. So those are 37, at least 37 times when at least one drone video was captured, and then a comparison measurement was captured with either an ADCP or a flow tracker, depending on the river, or salt dilution, actually. So now I'll go into some examples. This is a site in BC. You can actually see that there's a cableway going across, and there's a RP30 surface velocity radar on here as well. A lot of cableways have been decommissioned across the country for safety reasons. There just wasn't enough maintenance. And so in a number of sites where we used to be able to measure discharge from the cableway, that's no longer an option. And so drone videos have a lot of potential to fill in that gap. And so this, in this example, we took a measurement with an ADCP, the RP30 radar, and then also image velocimetry. And we used the surface velocity profile from the ADCP and the cross-section bathymetry from the ADCP as well. We're testing different software. Lately, we've been using HydroSTIV more frequently. We found that it's just fairly robust, just in terms of, because what we ultimately care about is discharge and queue, and it's just been robust and easy software to use. So this is what it looks like processing. And then for comparison measurements, we got a discharge of 160 cubic meters per second. The ADCP was 158, and then the RP30 was 163. So this is a case where all the technologies worked really well. Another video was taken about a month later. This is what it looks like. All the same instruments were used, but the cross-section and velocity profile weren't used for the purpose of image velocimetry. The ones from the previous visit had been used. So kind of like a blind measurement, only using the video to do the measurement. And we got a discharge of 98.3. The ADCP was 94.3, and then the RP30 was 90.4. So again, good agreement. This is things are working great. This next case is an example of there was actually large flooding in the province of Manitoba earlier this year. This is the Red River, and it starts in North Dakota in the USA and then flows up into Canada. And so we took the drone out and started doing some measurements. In this case, we weren't actually able to fly nadar view because we weren't able to fly high enough to get a nadar view. So this is where we did an oblique view. So with image velocimetry, we measured a discharge of 2580, and with ADCP, we measured discharge of 2040. So there's basically a 20% error there, which isn't necessarily that great. So that begs the difference. Why the difference in discharge? On the field notes, the tech noted that there's was a fair amount of wind, around 20 kilometers. Now that's just a guess. And they said the direction blowing downstream, that's easier to pin down. And this is where it gets into alpha coefficients. This is a normal flood profile where alpha is typically 1 for a river like this in flood. But with wind, you're going to get skewing of the surface velocity, which will then skew the alpha. And so I did a comparison of actually one of the S/S panels from the ADCP, basically in the middle of the river. And so this is velocity on your on the x-axis, and then depth on your y-axis. And the blue is the ADCP measurements, velocity measurements, and the orange dot is the image velocimetry surface velocity. And so basically what this is showing is that the wind is skewing more or less the blanking distance of the ADCP. And so capturing the alpha coefficient just from your ADCP isn't sufficient in this case. And so you basically need to adjust your alpha coefficient. So we adjusted that based on data from the surface velocity radar as well, got an alpha of 0.8, and the measurements match up much better. And the question I have kind of is for operations is how do you, when you don't have that ADCP comparison discharge measurement, how do you correct for wind? So we've bought some of these wind velocimeters, and we're hoping that we can record actual wind speed near the river surface and do a correction factor for that. I haven't really investigated that, and I'd be curious to hear what people think about how they correct for wind when it causes issues and whatnot. Next case I wanted to bring up is just kind of angles for mobile image velocimetry measurements. So these two videos were taken basically 10 minutes apart. The top is nadir view from a drone, and then the bottom one is a just taken from the bank with a cell phone camera. And I see one of the cell phone camera video is not working on the slide right now, but you can see that there's a lot more surface texture on the cell phone camera just by eye. And when I process that in HydroSTIV, this is just the auto deep learning algorithm, completely uncorrected. It doesn't capture the videos or the velocities very well at all in the nadir view. Whereas with the oblique view, it captures the velocities quite well. They're nice and stable. We get a very reasonable discharge. However, when you do go and manually correct the STIV images in the software, the velocities turn out much more consistent, and the final discharge is actually very, very close. This site is actually, it's kind of unique. Well, I think what was causing some of the problems is there's a lot of weed growth in the bottom that you can kind of see. And I think that was giving the software some issues. And so kind of the question I have is, how can we develop guidelines as to when it's worth taking a nadir video versus an oblique video? Because obviously the ground control points are much easier to set up for a nadir video. So we went and did some tests. This is another site in the mountains. On the top left, we have a nadir video from a drone. On the top right, we have one looking upstream, again from a drone. On the bottom left, we have one looking downstream from the drone. And then we also have a fixed camera at this site, and so that's on the bottom right. And went there, took a measurement, or so with all these videos. These are the discharges, 8.3, 8.26, 8.37, and 8.5. And the S by S ADCP measurement was 8.41. So all these measurements are within basically all these measurements are less than 2% error, which is great. And so this is a case where perspective didn't matter, and they all worked out really well. So in conclusions, we've seen image velocimetry work in many scenarios. Anecdotally, STIV has generally been more robust and faster than LSPIV for the purpose of obtaining discharge. Challenges still remain in operations. So windy conditions, when and how do we correct? Low surface texture, how can a tech determine if a measurement has a high chance of success? And then just procedures around drones, regulation, training, safety. And what's next for us? So we've got 1 more year of data collection and analysis, and then steps into implementing this into actual operations, as it's just in the beta testing phase. So that's it for me, and I'd happy to take any questions if there's still time. I realize some time was taken from getting the technical issues sorted out. So thanks everybody for your time.
Thanks, James. So first, if we can invite any questions from the online community.
None. Yeah.
So, do you want to come on up and provide your question? Thank you.
Hi, James. Sorry, probably I'm squeezing 3 questions. I saw your drone videos moving. Did you stabilize? In your third example with the oblique angle, looks like not a 1D flow. So did you check the issues of using STIV? And the fourth example, there was a lot of width, and you correct. So which alpha coefficient did you use there?
Okay, so sorry, the third video, stabilization, is that this one you're referring to, Salvador?
In general, I see all the videos from the drone. There is a bit of movement in almost all of them.
Yeah. Generally, I've been stabilizing the videos, but actually hearing Mark Randall's presentation about how often you'll you'll lose data resolution or pixel resolution when you stabilize the video. It's causing me to second guess that. And so I don't know the answer for that. Ideally, we'd have a great, easy to access separate image stabilization software so that we can then stabilize the videos and then compare all the different softwares. That would be my wish. And for the, I haven't, you were talking about, was it this video about different, that flow might not be perpendicular necessarily?
So that one is more because of the width. It seems that you match very well the discharge, but there is a lot of vegetation. And the previous one is because of the 2D and using STIV.
Yeah, so both these values, this isn't, we didn't actually have an ADCP measurement at this site. And so both these values are just estimated, or they're calculated from image velocimetry. And so they're not actually comparing to an independent ACP discharge. And basically, the alpha value is 0.7 here when and I calculated that just by comparing it to the rated discharge, because the weeds obviously do cause a lot of complications for that. And then I guess the last video, yeah. So that is a very good point. I haven't tried it in LSPIV, but this would actually be a very good case to analyze in LSPIV as well, because you have a lot of, particularly on the far bank, you've got a lot of eddies here and backflow. And it's just been, I haven't gotten quite to it yet.
Wonderful, thank you, James. We'll have to just call it a day there. Thanks for your contribution and thanks for the question as well. So we can now hand over to our keynote speaker, Edwin Cohen. So it's over to you, Edwin, and welcome.
Thanks so much for having me. And just a quick note on, I have two names and people get sometimes confused by it. So you hear many people call me Todd. It's an unofficial name, but everyone who knows me calls me Todd. So since officially I'm attending a conference, you've all met me. So feel free to call me Todd, but I do publish under Edwin. So I usually respond to both, but my mother's the one who usually calls me Edwin, or the tax services of the United States. Let me pull up my presentation here. Let's see. All right. So hopefully you can all see my opening slide.
Yeah.
Great. All right. So, first of all, thank you to Nick for organizing this conference. Thanks for the lovely invitation to present this keynote and give you some thoughts, perhaps, as we close out what's been a fantastic 2 days for us online and 3 days for all of you in person. And hopefully going forward, this workshop continues and my group and others will get a chance to all get together. Academically, a little hard for me when I'm teaching. So Nick, we got to talk in advance next time and find some times when I'm not teaching so I can be there. I've been in the sort of quantitative imaging game really since the early days of my PhD. In fact, when Nick invited this talk on short notice, I was like, wow, what can I do that's a little maybe different than what my group's presenting on infrared. And Erica's done some lovely work with me over the years and now has gone on to develop her own approaches, and it's really exciting to see some of the work she's bringing in. It got me thinking about sort of the history of why several people in my group, and most recently, most of the focus is on working with these remote sensing applications, whether it be in the lab with large scale PIV or in the field now, both with LSPIV and infrared. And the neat thing for me is it was literally 30 years ago this year, I think, that I first started playing with this. Might be 31. So 3 decades. And what have we seen? First of all, there's been a ton of people that have funded the work over the years. And so I'm not going to go through them, but you get a sense of it here. These techniques, as many of you have brought up, are of broad interest for a variety of disciplines. And so there is just a ton of funding. And of course, COVID being the latest, where we've seen lots of applications of quantitative imaging, trying to understand how things circulate. All right, why am I not advancing? There we go. So first of all, what's in a name? We've seen lots of names. We've had new names introduced to me during this workshop. I'll say guilty of introducing new names as well. That has both advantages and disadvantages. Of course, the names often come from our desire to differentiate subtleties in how we process images and how we track material. But it also means that if we start trying to look through the literature, we can struggle to understand which groups, which people, which disciplines are working in areas that are relevant to the kinds of work we're doing. And sometimes we end up reinventing the wheel. So it can be helpful to get a sense for what the history of the names are going back. Here's just a few when I give talks on general quantitative imaging techniques. But for me, as I say here, it's all QIV to me, or quantitative image velocimetry, because in the end, what we're doing is taking images and trying to extract velocity vectors from them. So we're doing quantitative work with these images. And I think as we think about these techniques, there are lessons to be learned from all of them as we try to apply them to do the kind of task we're interested in a better and more accurate way. So the big differences are, what's being tracked, and obviously we can track particles as we see in LSPIV. We can track individual tracers, or we can track clouds of those particles, so correlation versus tracking techniques. Increasingly, my group's been back at something I started working with back in the 90s, which is tracking scalar patterns. Back then, we did a lot of work with fluorescent dyes, and we thought about, how can we extract the velocity field from those dyes while using the dyes to get concentration, laser-induced fluorescence, if you're familiar with it. But of course, it's the same trying to track temperature. The only difference is dyes, we put into the water temperature patterns, as we've seen from the incredible images that both Seth and Evan have put up, are always there. They're omnipresent. But you also get, as many of you are now using, particularly those working with the LSPIV, all kinds of patterns in reflected light that aren't actual particles, but actually you're tracking patterns, whether they be on capillary wave, gravity waves, or other surface turbulent induced refraction and reflection of light. And of course, how we track them also often differentiates what's in our names. And there are lots of examples of different approaches. Obviously, correlation is at the heart of many of these LSPIV techniques and different versions of it. Phase correlation. We're working in minimum quadratic difference because it lets us track both dark and bright patterns simultaneously. So in temperature, we see that. And of course, phase correlation will do that, but traditional cross correlation doesn't. But if you're into particle tracking, then you're looking at how do you actually track individual particles. You may get into nearest neighbor algorithms or probabilistic approaches, Kalman filtering, as Erica and Giulio have shown us, FFT and spectral approaches, really valuable for extracting things in phase spaces, particularly if you're trying to get at the dispersion relationship and other aspects of trying to track surface features. And increasingly, deep learning, neural networks, and machine learning, areas that I think my fourth decade will be dedicated to try to understand the powers of, are demonstrating that they can really be efficient and robust techniques to extracting all kinds of information. And finally, hybrids really have become increasingly popular across multiple aspects of these approaches. But in the end, we're all simply tracking some pattern. And the question is how we do it. So I'm going to turn back to images I've been using to discuss this for really the better part of these last 3 decades. And so here is a classic synthetic PIV image. And I'm looking at what I call image F and image G, sometimes image 1 and image 2. Obviously, in majority of these techniques, we're comparing displacements across 2 images. So the first thing I always do, and I like to remind all of us, is, I subtract the images. And if I can see motion, as you see here, black to white, and there's clear evidence of this rotation coming through the flow, I know that I've got something I can track and train a computer algorithm some way or another to do it. And so then the question is, what do I use? If I look at the sub-window level or the sub-region or sub-area window, we all have our own names for what we call these interrogation regions. I can extract that displacement, for instance, using a cross correlation. So here in the 2D plane, here in the 3D plane, showing cross correlation. Nice thing about cross correlation of particles, it leads to these very narrow correlation peaks. which we now can extract an interdisplacement from. That displacement here on the order of a few pixels in a 32 by 32 pixel subwindow is great. It gives us, a couple pixel displacement. But the resolution then is, sort of poor on the order of, 1 part in 10 at best, 10 pixel displacement, maybe in a 32 by 32 subwindow. So our accuracy is only about 10%. So then we get into curve fitting these peaks to try to pull out sub-pixel accuracy. I'll have more on that in a minute. But other techniques come up with other approaches. The MQD method that I just referenced, the minimum quadratic difference, looks really at a minimum shape. So a bowl, here I'm showing only the 2D, but this is now a low point in the image. It has a much larger spatial scale, which depends a bit on the kind of features you're tracking. But here I'm actually tracking sediments that have been illuminated by a camera on a distal tip of a borescope. And so what we see are sediment grains going by the tip of the borescope. So black features and white features, depending on the granular material. We want to track both, is why we went with MQD. But you see the scale of those particles are quite large, leading to a very large minimum region. And so here you can start sort of questioning, how do I track that subpixel location? You can see we're reporting displacements at a subpixel accuracy. And here we're using a center of mass technique because it turns out this has less of a bias when you have these very flat bowls. But there's always lots of questions about how do you do these subpixel fit schemes to improve the displacement accuracy. In some sense, if your goal is mean flow, maybe that's less important, because like you would with an ADCP operating in, say, if you speak RDI or Teledyne, mode 1 or mode 12, then you can take lots of measurements that are relatively noisy, if you will, so discretized and integer pixel displacements, but by averaging them, you now get a very nice mean that is accurate to, to probably 1% or better of your subpixel fit. But if you're interested in turbulence, this instantaneous ability to track these displacements to subpixel accuracy is important. So many of you are working in LSPIV, and in LSPIV, of course, we need tracers, and sometimes those tracers are present, but often they are not. And I've seen some incredibly innovative approaches to solving the tracer problem. I think my favorite is the Rice Krispie trees from a drone that leads the camera-based drone heading down rivers. But when I started playing with these imaging techniques, I got really interested in particle tracking versus correlation-based or PIV techniques, because when I look at an image, I see all these particles, like I show in image F here, what I've got 6 images in my little synthetic image. Yes, I can get one vector out as a correlation, but I could get 6 vectors if I could track all of them. And in fact, as someone who's interested in turbulence historically, the challenge I have with any correlation-based technique is we get shear-based decorrelation. Turbulence is full of shear. It's well known that shear decorrelates any kind of correlation-based technique. That includes acoustic techniques. It includes laser-based techniques. For those of you who've worked in those spaces, anything with a volume is subject to shear, and shear will lead to decorrelation. Talk a bit more in a minute about how we solve some of those problems, but one simple solution is, if you can get a crude estimate, and by crude, I mean a pretty good estimate still, based on PIV of what the average displacement is, well, now I can use a predictor corrector algorithm and predict the displacement of every particle in the subwindow based on that mean PIV-based estimate, and then draw a very small search radius around that location and ask myself the question, is a particle in that search radius? And if I've got a pretty good estimate and the turbulence is, strong, but not insanely strong, then that search radius is small compared to the mean displacement. And I can confine my search radius to a region that ends up being only about 2 pixels and very effectively find all of these particles. And that's what I sort of first started doing in the 90s. That's what is really sort of the heart of Cowan and Monosmith, the first publication I have in this space. And it gave us relatively high density particle tracking algorithms But in that, you end up with a problem that your particles are now at random locations. They are where they are, and you have to think about, how do I use data that is randomly located if you're interested in then trying to go back and calculate higher order metrics like spatial derivatives and instantaneous gradients. But there are techniques to do that, and it's something to keep in mind as we increasingly are tracking things on surfaces, that particle tracking may lend some solutions to some of the problems we run into, and in particular, shear decorrelation can be one of them. All right, but this group sort of really focused on surface velocimetry. So why should we care about all these details? And in fact, as many of you have presented, and I am now fully convinced, space-time image velocimetry rocks, right? It does just an amazing job. It's very robust. It's very computationally efficient. And if you're interested in getting the mean velocity transect like you would with an ADCP, it is hard to argue against STIV being the approach of choice if you're working with these surface and remote sensing techniques. But as has come up in over half the talks, what if we don't know alpha, the velocity index, and what if it's varying in Y? And these flood conditions, we see strong variation potentially in what the boundary layer is looking like as trees and shrubs get flooded, and we jump our channels, or if macrophytes start showing up, as the previous speaker mentioned, a huge problem in many of our shallow flow systems. We often don't know the bathymetry. We've seen examples where the bathymetry is highly dynamic in a French alpine stream, and in fact, the bottom got above the region where the remote sensing instrumentation was able to see water, and so you're looking at just dry land. So what if we need to calculate that bathymetry? And we're interested in, did the bathymetry evolve? What about the bed stress? Was the critical bed stress exceeded? And do we expect there to be incipient motion and large motion scales on the bottom boundary? And can we use information about that to ask ourselves a simple question? Should I go back out there with a ground penetrating radar or a survey team and resurvey that bed? Or even more, can I use my remote sensing to actually estimate what that bathymetry is? And then finally, as Evan mentioned, and I think as many of us are working on in projects outside the scope of this conference, gas transfer at water surfaces is a huge unknown piece of what's happening in climate change. CO2 is obviously the elephant in the room, but increasingly methane is being recognized as the order one challenge in many of these natural systems as we have decomposition and microbial transport and respiration. And then in general, what about turbulent transport processes? We've just had this horrific hurricane flooding, Hurricane Ian in Florida. There's a huge concern about what was in the floodwaters that are being transported around. Where did all that stuff go? How did it disperse? Remote sensing from drones, from satellites, from fixed cameras has a lot to answer in those spaces. So this is, I think, why many of us actually care about, more than just getting at the Q, the mean flow, where I think STIV is the workhorse potentially going forward, but there are other pieces that we want to get from perhaps more highly resolved turbulence measurements. So my argument is that, two-dimensional PIV type techniques, two-dimensional QIV that is temporally resolved lets us get at most of this. So let's take a shot at answering many of these questions. The first half of the topics I want to touch on quickly are sort of the history of how we've improved the various aspects of lab-based quantitative imaging. And the second set is just a reminder of really work that Erica quickly summarized in one slide today, but that she presented last year, and touch on what we've been doing in gas transfer. So one of the things that we've been doing in the lab forever, and I think is something that perhaps many of you are already doing on your field-based techniques, but if you're not, is something to consider about, is what I refer to as dynamic subwindow location. So we consider, these two subwindows that I'm showing below. If I look at, say, image 1 or image F, and then this is the original location of those particles. I should have done them in more of a deep purple or something, but they've moved in the flow field to this image on the right. Then if I use my subwindows in a static location, clearly delta T, the time between subwindows here, is large enough that some of the particles have left the subwindow. So I have a downward bias or a negative bias, or what's often called a gradient bias, that shows up because my algorithm will track these couple particles that remained in the subwindow, but those that left will not get tracked, and it'll underestimate the mean flow. So how do I resolve that? Well, I just shift the subwindow. I let the second image subwindow move, and now I capture all the particles that were in the first image. So this is known as a discrete window offset, and it allows us a combination of higher resolution and better accuracy. And in fact, we can work with smaller subwindows, is why we get higher resolution, because I don't need a large enough subwindow to actually capture that entire displacement. I could have taken that initial subwindow, and if that was 32 by 32, gone to say 64 by 64 or 48 by 48, and I would have encompassed the entire displacement, but then I'd be averaging over a larger spatial scale. But the reality is strong shear does lead to decorrelation. And in fact, if I look at these two subwindows, I see a case of stronger shear. I have particles that have moved out the left-hand side and out the right-hand side. So I again get my gradient bias. But I also perhaps have just total decorrelation. Perhaps everything just kind of breaks down here. How do I resolve it? Well, the classic way to resolve it in both, PIV type techniques or in acoustics is to work with a smaller delta T, allow the shear to operate over a shorter time. The displacement gradients are smaller, my gradients are smaller, and life gets better and my decorrelation disappears. The downside is if the velocity field is not very strong, then my overall displacements are smaller and my uncertainty can go up. So it's not always the optimal technique. And in fact, another technique, again, really lifted out of acoustics, is to shrink our interrogation region in the direction of the gradient. So here we've got a du/dz showing up if I call z the vertical. So I shrunk my subwindow in the z direction, and I now have a much smaller gradient or displacement gradient within the subwindows, and I'm able to capture all the particles. And of course, I would get twice the resolution because I'm now going to draw a second subwindow below. So shrinking your subwindow in the direction of the shear is a powerful way to become more robust against these challenges. Finally, one that I've been talking about for 20 years, but we've never actually implemented in our own codes, and maybe I can convince Seth to do it, and or one of my students, maybe Evan, this is going to be your task on our codes, but is to actually deform the subwindows. Right, if you deform the subwindows, now you can track all the particles and there is no shear. I make the side of the subwindow that is being deformed, I let it deform in that direction itself. How would you go about doing this? Well, you do it by interpolating the image. And historically, that's been expensive and maybe a little scary for those of us in the lab. We do some interpolation, as I'll talk about in a minute, in our laboratory approaches. But obviously, for those of us who work now in the surface imaging fields, interpolating images is kind of a bread and butter if you're georectifying images. So we're already doing this window deformation. And so I would argue that if we've got highly sheared flows, this is easily in our wheelhouse to be doing and something we should all be thinking about. So a question that emerges in all this is, where is a vector located? So in time, we're basically doing a central difference, right? We have an image at time 2 and an image at time 1. We basically look at the correlation between the two, and we would argue that the time of the measurement sits squarely at the center of those two times. So say, T1 plus delta T on 2. In space, a central difference would be the most accurate again. But for those of us that started by using some sort of discrete window offset and letting subwindow 2 slide based on a fixed location of subwindow 1, we're really then locating spatially the vector at the interrogation grid point that we started subwindow 1 at, then displaced by some random displacement measured between the two subwindows divided by 2. So now I've got a perturbation to my interrogation grid that I either have to interpolate back or I have to think about some way of solving. An easy way to solve that is to now use a dynamic subwindow algorithm that actually displaces the subwindows in image 1 and image 2. In image 1, I displace the subwindow half the delta X and delta Y that I'm measuring, upstream, if you will. And in subwindow 2, I displace them the other half downstream. So then I now have a displacement that is the integer pixel distance between the two subwindows. And I now expect all of my particles to effectively be in the subwindows. And really, I'm just down to subwindow fitting. And this is actually what we've been doing forever in our laboratory-based techniques. We actually allow up to 5 passes as the subwindows move around to try to find this position where the subwindows are now located dynamically, 50% upstream, 50% downstream, relative to whatever interrogation grid point we've chosen. So I'm central differenced around that grid point, and I have my integer pixel displacements accounted for. And all is left to do is solve for the subpixel fit. And so we then have a dynamic multipass algorithm. If we have no initial estimates, we often work with a larger initial subwindow. From that, we get some displacement. Maybe that's a 64 by 64 or even larger subwindow. We get some initial displacement, 12 pixels. We then feed that at the subwindow level into a next pass so that every subwindow has its own unique displacement. And we can continue down that set of passes. We can enhance the resolution and work our way to a final displacement. If we have an initial estimate, like many of us do in surface PIV, we know the river's running, left to right in the image or in some direction. We have a boundary layer perhaps, and so we know with some accuracy what that initial displacement is. We can start with that initial displacement and continue down the same road. So this leads us to the subpixel resolution. PIV traditionally works with Gaussian fits. It turns out you can decouple this into a 1D problem in both directions, and you can very quickly just fit for your subpixel fit, where 0 here represents the integer pixel peak, and then I look to the left and to the right, and I find what the values are, and then I fit my Gaussian. The challenges with all this is when we do subpixel fits, whether we're using Gaussian, center of mass, parabolic, we end up with a bias. And so here I'm stealing some work by Jerry Westerwheel, who did a phenomenal job with analytic PIV. So 0 is the integer pixel location. So if I happen to have my peak sitting at 0, I have no bias. But if I start to move in the positive direction, let's say I have an integer pixel displacement of 0, but my subpixel, my real displacement sits at 0.3, you see that regardless of technique, I have an error that is a bias error. And that bias error, if in the positive side of the displacement, is in the negative direction. So I'm biasing my measurement back. And by biasing it back in the negative direction, I am tending to move my subpixel estimates back toward the 0 pixel location. This is known as peak locking, and laboratory-based measurements are full of it. So here's a laboratory-based measurement. I see my integer pixels. I have not calibrated these images, so these are displacements in the negative direction. So big, strong peak at -10, big, strong peak at -9, big, strong peak at -8, strong peak at -7. This is what happens. Really, we know that the histogram here should be essentially Gaussian, like it would be in turbulence measurements, but we're not seeing it. How do you solve it? Well, first, does it happen in surface velocimetry methods? I can speak to IRQIV. So here I grabbed Seth's measurements that he briefly touched on in his talk on Monday and presented, he and I both presented last year in Sutter Slough in California. And here you see the integer pixel peak locking happening again, 6, 7, 8, 9 pixels in the negative direction. We see it less in the vertical direction. You see a little hint of it, but here the displacement range is much tighter because the flow is dominantly in the X direction in this case versus in the Y direction. So how do you solve it? Well, you solve it by doing, ironically, interpolation again. You can interpolate the images so that you can basically move the displacements so your subwindows are located perfectly at an integer pixel distance for the displacement that you have. I turn 10.3 into 10.0 by interpolating where my subwindows are. And so here, A, the red is the original Gaussian case. I think these might be mislabeled, actually. No, that's right. A is the original Gaussian. The red is the Gaussian case. You can do in the spatial temporal fields, you can do bilinear or bicubic to interpolate. What my former student Chen Liao showed during his PhD was that actually we already are working in the spectral domain to do the correlations. The interpolation is much faster in the spectral domain, and in fact, it's much more accurate. So in the spectral domain, we can work with a variety of techniques, the green, the red diamond, and the blue triangles, D, E, and F, all of which essentially eliminate the peak locking. And so here's an example of the original Gaussian subpixel fit. Here's the bilinear and bicubic. But if we move to the spectral interpolation methods, we see that we recover essentially the Gaussian peaks, eliminating the peak locking. So we haven't yet applied this to our surface velocimetry techniques, but as we push deeper into the turbulence, this is going to be an important aspect of improving our calculations. And so turbulence. Right. So in the lab, we've been measuring turbulence really accurately for a long time. Here's a turbulent velocity field at a scale of 50 centimeters on a side. I've removed the mean flow. You can clearly see it advecting these eddies. We can do these beautiful turbulence measurements in the lab. And of course, Seth has shown us that we have the incredible same set of features happening on river surfaces, whether you're revealing them with infrared or you're putting Rice Krispies or other, flotsam and jetsam out there, or looking at the backscatter from gravity capillary waves, they can be revealed in our surface imagery. So with these surface turbulent structures, what can we get at? Well, last year, Erica did a wonderful job of walking us through the 4 papers she put out. And in summary, one of our holy grails, of course, is bathymetry. And to get at bathymetry, it turns out that those large eddies that you can see scale with the integral length scale of the turbulence. So if we look at those integral length scales, we can actually correlate them to depth. And Erica found that the transverse length scale measured, transverse velocity length scale measured in the longitudinal or streamwise direction, what we call L221, tracks beautifully and has high resolution in the lateral. And so, in fact, sort of good enough for government work. Basically, what we find is the depth is about twice the integral length scale of the L221 length scale. And so you see here, there's a subtle difference in the rough and smooth bed. That difference is subtle enough that certainly first cut, the first order is multiplied by 2, and you've got your flow depth based on that scale, and that scale can be resolved locally. So then the question is, okay, can we get at this bed stress from surface dissipation? And Erica went after the entire dissipation profile to do it. She leveraged the work of Nezu that goes way back into the 70s, and took his empirical results, which have this empirical coefficient E. He set E at 9.8, but he basically gets a non-dimensional, power law type profile based on the non-dimensional depth. And from this, you can solve for the bed stress or the friction velocity, however you want to parameterize it. The key is you need the surface turbulence. And so you can get at surface turbulence lots of ways from surface dissipation. You can get at it from surface turbulence. You can do it lots of ways. In the lab, we've historically done it directly, and direct measurements really go about resolving the fluctuating strain rate tensor. But to resolve surface dissipation directly, you need to be down at order the Kolmogorov length scale of the turbulence, maybe at 10 times that. So you're talking millimeter scale, maybe getting up to centimeter scale in weakly turbulent flows. But let's be honest, the flows we're looking at in flood stage are incredibly turbulent. So you're really talking millimeter scale. So unless we see the next evolution of cameras getting us to 10K by 10K videos, I don't see us getting at millimeter scale on surface PIV. So my current thinking is direct doesn't really have a whole lot of power for us in remote sensing. But second order structure functions and spectra do, they resolve the inertial subranges of the turbulence. As Erica showed an hour ago, she's seeing a nice minus 5/3 region in her turbulence. That is the inertial subrange. From that, you can back out spectrally the dissipation, or you could use a second order structure function approach to back out the shape of the second order structure function, from which Kolmogorov's 1941 theory also shows us how to back out the dissipation. So 2 publications that I've worked on that we've compared some of these techniques shown here, but any good book on turbulence, Pope 2002, or Lumley's book will show you the directions to do that. So that gets at how do we get at Nezu's empirical E? Well, again, you know, we turn to Erica Johnson, who figured it out as the final piece, really, of her thesis. You can measure the surface turbulence, and she calculates URMS. She does some corrections for the surface velocity scale and the URMS based on what she needs to get at, but she turns to Nezu again to look at his empirical constant for the streamwise RMS turbulent fluctuations. And from that, she can solve for E, which, using Nezu's 1977 results, comes from this estimate of the streamwise empirical constant D sub U. And so that then gives you your ability to get E. And from there, we get after what I think has been a theme through at least 50% of this workshop's talks, is the unknown quantity alpha, or the velocity index. It strikes me in watching all of you talk is that we are down, you know, easily making measurements of the mean surface velocity transect using STIV or LSPIV techniques at better than 10%. And once we get to there, then the uncertainty in really bathymetry and in the velocity index alpha become the leading order error. And so how do we resolve that? And the way to do it, you know, is to try to get at it directly from the surface flows. And so Erica showed that, you know, we have an understanding of what alpha is, and it, you know, can be sort of traced to integrating up a boundary layer model, and the power law works pretty darn well to much better than 10%, getting us order 1% accuracy. She, you know, as her incredible skill, as she showed us, she goes through the literature and leverages what people have done before us, and she noticed that the shape factor, this ratio of the displacement thickness to the momentum thickness, which really gets at how is the vertical turbulent mean velocity profile being mixed out. It's more mixed out when the turbulence is strong. It's less mixed out when the turbulence is weak, but it's also more impacted by things like macrophytes or very rough beds that leads to very different power law profiles and different values of M. And so it turns out the ratio of the momentum thickness to the displacement thickness scales with this M, and she leverages that and shows the correlation from her own data. So here's the shape factor, not to be confused with flow depth, versus M. And from that, you can now predict based on surface turbulence what H is. From there, you can get at M. From M, you can integrate up and get B. And from B and your surface velocities, you now have alpha. So you can directly measure alpha as a function of Y, your transect. So you have a resolution in these complex flows or compound flows where alpha is varying with the width of the channel. And of course, she shows us you can put that all together. You can take your mean surface velocity profile, your power law, get to your depth average velocity profile. Then you can take your integral length scales, get to your bathymetry, and get your local flow depth. Combine all that, you get flow rate, and you do an incredible job of actually predicting flow rate. The final piece I want to talk about is measuring gas transfer. I think it's something we all ought to be thinking about as we're making all of these measurements. And one of the huge uncertainties as we move forward is what is going in and out of water surfaces. And so McCready et al. Back in the 1980s came up with a surface divergence model. We've found so far in our lab, it works really well on predicting gas transfer. It does have an empirical coefficient C, but basically it leverages the surface divergence. So here, if we could define beta as the surface divergence in 2D, it's really then dw dz. And so we can then take the RMS surface divergence, we call that beta prime, and we can directly measure it from our instantaneous surface velocity fields. So here, Veronica Citrone for masters did this in our lab. In the top, she's doing just a classic open channel laboratory flow with a smooth bed. In the bottom, she's perturbed the bed with ridges, and she's put those ridges in actually to enhance surface divergence. And so you can see the surface divergence strengthening over the ridges. The ridges are over the even numbers of the Y on H being flow depth. And so you can see these surface divergence accelerations, but these are the exact same flow speeds. She here mentions the flume frequency, but these are mean flow speeds in the sort of 5 to 10 up to 30 centimeters per second. And so same flow speed, much higher surface divergence, which leads to much stronger gas transfer. And so here she's got the no ridge case. Here we have the with ridge case. And you see the McCready et al. Model predicting her measurements, which were done by purging the flume of oxygen and then just letting DO re-aerate back into the flume. So these are oxygen measurements, but you can use whichever molecular diffusivity you need, in this case oxygen, but CO2, methane, to get at the gas transfer velocity for whatever low solubility gas you're interested in. All right. Hopefully I haven't gone too far over, but I'll end by saying, imagine all the information we can measure in environments where we get images like this, and we're all getting these images, whether you're working in the infrared or you're working in the visible, you are revealing these structures and you are tracking them. Some of us are averaging them out to get mean flow, but many of us are increasingly interested in leveraging those surface structures to get at all the other pieces of the flow rate problem and beyond that we're interested. And I'll stop there and thank you all for the invitation to address you.
Okay, thank you very much, Todd. We'll go with questions in the room in Lancaster first, please.
Well, Michelle, can you hear me?
Yep.
Oh, can you hear me? Okay. So have you taken into consideration, you talked about velocity gradient tensor, so the wall normal components can have quite an impact. So have you looked at any methods which you can capture that? So holography or tomography or anything like that to see if you can better those results a little bit?
So you mean and sort of things like the du dy coming off the sidewall boundary layer?
No, coming from the base, so the W component.
Ah, yeah. So from the surface, of course, the best that we can do is get at gradients in W through the divergence. You can integrate those up to start to look at what the W field looks like. We have not played with that much, but it's a really interesting point, and it is, I think, something that could be done.
Yeah, there's some work, John Hopkins with Joe Katz's lab, and this is pretty cool stuff with holography. So I don't know if you've seen that. That's some neat stuff with inline holography.
Yep.
Nice.
Okay, someone in the chat.
Okay, we've got a question in the chat.
He put his hand up on the Zoom, so
Hi, can I ask the questions from the online?
Sure.
Okay, thank you for the presentation. So I'm very interested in the estimating the water depth from the velocity distribution. So did you estimate the water depth in the field? For example, the video showing here. I try, and some coefficient is not universal for the laboratory scale. For the field, some adjustment is needed to quantitatively obtain the water depth. How do you think, and do you have some experience regarding that?
We do have a little bit of experience, and that's probably something that will be growing significantly in the coming year. But the work I presented last year in California, we did back out the bathymetry from Sutter Slough from the turbulence field, and using the technique that basically that Erica developed, and it worked really well. The key really is that you need to have a technique that's resolving at least the larger scale eddies. You can see them here, and it's pretty clear that in an unstratified flow that they are representative of the flow depth. And so the main issues that can impact it would be some other shear layer. And so the two that are particularly come to mind would be if your flow is stratified, so deeper rivers and in low turbulence conditions, or as we saw in the previous talk, macrophytes can lead to a very strong shear over the canopy, and you'll get a false sense of what those scales are. But if you have a relatively well-stirred flow with, without macrophytes, it works quite well.
Oh, okay, thank you so much.
Thank you, Ted. It was very informative talk. I just wonder if somebody, including yourself, has done any work to explain the physics underpinning the actual nature of the processes which cause the images shown in the current slide, you know, the thermal imaging.
Yeah, it's a great question. So there's a ton of work, of course, on this. I mean, it gets at, you know, turbulent heat transfer. It also gets at sort of the surface latent heat fluxes and the constant budgets that are going on. And in fact, the gas transfer community has thought a lot about this. One of the key models for you know, gas transfer is what's known as the thin film model. As I'm sure you're all aware, the surface boundary layer here is really, really thin on a free surface. We don't have the no-slip boundary condition. We have the dynamic free surface boundary condition and the kinematic conditions. And so the eddies are splatting because of the kinematic condition. The dynamic free surface boundary condition leads to straining of it. And that very, very thin boundary layer really kind of, much like any boundary layer, starts to interact with the turbulence and suppress it. And so in the end, the top hundreds of microns are where the processes of heat transfer with the air are happening. And you have this tremendously thin but strong thermal gradient happening across it. And you have tenths of a degree C differences in this region. And the sort of holy grail in gas transfer is understanding how much time a parcel of water spends on the free surface, what's called the surface renewal time scale, because the longer it spends on the free surface, the more it becomes in equilibrium with the gas or the thermal condition. But then once it saturates to its you know, Henry's law gas concentration or thermal equilibrium, then until it gets stirred into the bulk, it's just sitting sort of not efficiently transferring heat or gas. Then the turbulence comes up and stirs it out, and I get a renewal event. And so, so it's pretty well understood. And in fact, there was a question earlier about how can we understand wind stress? And one of the pieces that I'd like to try, and in fact, it would be neat to get to some of these wider rivers where you guys are seeing windier flows. We have yet to be out in a windy environment, is actually leveraging this surface renewal feature to track wind flows. Because if I go back to what I just said, if I have an eddy that has come to equilibrium with the surface temperature, so if the air is warmer than the water, then warm eddies will be in higher equilibrium and have spent longer time on the surface, is my hypothesis. They will be more impacted by wind stress. They'll be moving with some inertia of the wind stress. Whereas an eddy that's just come up from the bed will not have seen the wind stress nearly as much. So it will have sampled the bulk velocity on the way up, but not have been impacted. So the difference in tracking the warmer versus the cooler eddies in that flow, so if I conditionally average based on the thermal temperatures, should be the difference in the wind speed. Much like Erica and Giulio and others are using, you know, Doppler shifting of waves, we could effectively use the biasing of the wind stress on water that has been resonant on the surface without being renewed longer to actually back out the wind stress. So I think there's an example of actually leveraging that physics to get at a quantity that is becoming of more interest as our techniques get so accurate that we're now seeing impact of the wind stress.
Thank you.
Okay, we just have one final question.
Yes, thank you, Edwin. My question is, do you think we can extract some characteristics of turbulence in a steep river with very irregular bed? I mean, in the streamwise direction?
It's a great question. And, you know, certainly watching some of the images come out of the French Alps, it reminded me of, you know, some of the things that, you know, Evan and I were seeing. He showed the upstream side of the flow through the conduit where things were very smooth, and saying he's going to try to do most of his PhD work on that side, because the downstream side that was highly aerated, you know, was a little scary to think about. How do we extract information from it? And of course, in steeper gradient mountain rivers or, you know, high flood flew through, you know, even, you know, bridges and places where we have these strong transitions in the free surface, we get a tremendous amount of air. And I think it's an open question about what we can do. You know, like any numerical technique, the danger of our techniques is they will always measure something. Stuff is moving, right? We can see gradients in the aerated flow coming around, the boulders and these very turbulent, highly unstable surface events. So we'll track something. What does it actually mean? I think that's the question in my mind. And it's really tricky because, of course, acoustic techniques fail there. It's very hard to ground truth these techniques. So I think we will probably have to turn to the lab to understand at least, are we doing okay, where we can measure, bulk flow rate by simply, we know how much water we're pumping through a pipe, and we can then create these very aerated flows, particularly at some of our larger facilities in the US. The US Bureau of Reclamation, for instance, has facilities like this, and we have some mountain stream locations that are actually manufactured sites where we know the flow rate. So I think we'd have to start there, but we'll measure something. And the question is, can we understand that physics enough, what the aeration is enough to understand how to correct for the fact that there's a lot of air there, and use that information then to perhaps even tell us how much air is there, what is the void fraction, to accurately estimate all the things we need now, including Q and how much water is actually underneath that aerated free surface.
Thank you, Todd, for answering those questions. We'll call the session to an end. The good news is it's now lunchtime. I'll thank everyone online for your contributions, and let's go to lunch. And where is it? Where is it? Is it just out there? Yeah. So yeah, thank you very much, and we'll just do a final congratulations. Thank you very much.
Thanks to all of you, and thanks to all the speakers. It's been a great conference. Enjoy the lunch and the rest of your chats.
Oh, cheers.